Okay, I shall start. So good afternoon or good morning. I am Tony. So I'm a professor at Singapore University of Technology and Design. So it's my pleasure to actually give this keynote talk. Unfortunately, it's virtual, but hope to actually physically attend the conference in the near future. So today I'm going to share on my perspective of AI in networking and communications. So before I go into my physical talk, just give me a few minutes to share my university. So SUTD is Singapore University of Technology Design, established in 2009, so it's about it's 10 years old. So it's a technology university focused on design, and it partners with the East and West. So in the West, we have MIT. In the East, we have Zhejiang University. So as I mentioned, it's a technology university, multidisciplinary, and we have partners all around the world. And it has a few awards. So it has actually been recognized as, in terms of global state of the art in engineering education, it's ranked as the top by MIT in this survey in 2018. And it's also ranked the top in telecommunications, and it's the only Asian university. And we have 4 areas: cities, aviation, healthcare, AI, that we are investing in our university's growth plan. So today I'm going to focus on AI. So you have an interest to visit our university and to understand more, you can visit our website or you can contact me. So I'm going to go to the technical stuff. So today, the keynote talk, I'm going to talk about three aspects. So the first aspect is on an overview of how AI recently has been used in the context of wireless communications and networks, and some of these topics and some of these preliminary results that we have done to show that the capability of AI or machine learning. And I'll end with a very simple conclusion, a conclusion that if this is going to use, if we think of it, let's say if we're going to use it in pre-5G or 6G, what are the issues that we should tackle in the future? So I'm going to AI in wireless comm. So as we know, wireless communication systems has been is a well-established system. So Shannon established Shannon theory in 1942. So we have since then we have accurate mathematical models, channel models, signal processing, receiver models in many scenarios, and that's the reason why we have a very stable, very reliable 5G systems, 4G systems, our handphone systems are working very well. And a lot of optimal solutions or efficient solutions are known for various situations like water filling and so on. Many design constraints to implement practical hardware, because actually this handphone itself is a very complicated system with many constraints. So the direction of what we see of AI we're going to use in such established sort of area in wireless comm, there will be 3 areas. First is our universal optimization framework for arbitrary models. So for example, as our models become more and more complicated, let's say I'm going to use it to incorporate satellite, space, incorporate underwater, incorporate multiple more complicated systems where we don't have a good understanding of the models itself. So could it help us to optimize such a framework? It could be used in a case where one robust to unknown prior information or missing information, as we see that there are more and more of new applications coming up in the future. IoT is one aspect where we may not have prior information. Better solutions for large-scale non-convex, because we'll see more and more non-convex problems, because in the past, usually when you design a system, you have a single objective function, but more and more in the future, you will see that actually it's not just a single objective function. Itself is actually it could be a sum of different objectives function. So if you have a sum, it's actually not so trivial, right? So weighted sum or more complicated QoS. So how would this be used? So recently we see some of these papers that appear in the past 2-3 years. For example, in the context of resource allocation, people use supervised learning method, train a neural network to predict WMMSE. So this approach, because it's supervised learning, so you train the optimizer to learn from the past. So what you can get the solution is as fast as what your training set is given, which is WMMSE. So this is a supervised learning approach. So this approach, the motivation is people say that if you do this, then you can optimize in an online fashion because it's really pre-trained. So it's sort of the optimizer will use a lookup table. So unsupervised learning approach is a bit more tricky because not necessarily will converge. So you have to be very careful of how algo is initialized, right? So there's some trick that you need to do for unsupervised learning. There's also interest in actually replacing our end-to-end communication systems. So traditionally, we have this transmitter, channel, receiver. So there are interest to replace this receiver, for example, OFDM detector or ISI with unknown ISI channel models or very complete massive MIMO channels, receivers or very complicated channel model. Can I actually, or channel decoder, can I replace this receiver design with neural network, right? So the neural network, if I pre-train it, very probably can I actually use a lookup table actually as to drive my receiver. So this is sort of a supervised learning approach. Beyond the receiver, people also looking at the joint transmitter receiver. So you can do a receiver, you actually can do a transmitter, you can do a joint transmitter receiver end-to-end design. So this can be used for RF communications, or you can use for even example visible light communications. It's actually afterwards I'll just show an example how this can be done. Actually, go beyond this. You can apply to other type of channels. So in summary, what we see in this few years, we see that resource management is an area that people are looking to replace neural network because replacing existing optimization algorithms with neural network because to reduce complexity, for example, to get better performance because the original problem is non-convex. If you actually apply this carefully, you can actually achieve a better performance. We'll see some example later today. Or transmitter receiver design, replace existing encoder receiver structure with deep learning. And you will see more and more applied beyond this physical layer or resource management to MAC layer or network layer. So because of the interest of time, I will not go through everything. What I'm going to do in the subsequent time is actually give you some examples of some preliminary work so that you can exhibit how AI can be actually applied. To do this, before I actually go into details of my preliminary work, I just want to share some research direction because there may be students or maybe researchers' interest. If I'm going to go into this area, how I'm going to make an impact because AI is dominated by a lot of machine learning and signal processing community. So from my personal perspective, there's 4 areas that I'm particular interest from a perspective of communication and network. First is this distributed machine learning or federated learning, because you can think of the context of a lot of applications in our network. You're going to have it's not really a centralized, it's distributed. So if you have a distributed, how do you actually do distributed machine learning? How do you want to do federated learning because of privacy of data? What is actually difference when you apply this approach, unlike the machine learning community, is that we have constraints. We have constraints like power constraints, we have constraints of backhaul constraints, our data is imperfect, we have latency constraint, cost constraint. So the key thing is that how do you incorporate all these constraints into algorithm design? So this is the unique part of our area. And applications like this has a lot. Edge for computing, if you want to do edge analytics in a scalable manner, how do you do? So there's the blue part is actually application. So this is one interesting area. We see a lot of works currently in the archive and in conferences. The second work is actually we really need to think about learning, right? You imagine a lot of all these learning models really depend on data set. But what about our interest is adaptive learning. In a sense, I will definitely not train it just for one task or train it just to send one type of data. So how can I make my system adaptive, right? Adaptive because traffic, right? Our network communication has traffic, cost, our data are missing data, different applications, right? So this will require a more innovative way of how you want to do learning. Reinforcement learning is one direction, but of course the complexity convergence is an issue. So we need to tackle this, especially want to apply this with IoT, massive connectivity, IoT network. So it's a massive type of network. So convergence is the issue, cost constraint is the issue, power is the issue. So we need to tackle this. The third part is data-driven learning. What I mean is essentially you think about the current approach of deep learning or AI. It's actually the data that drives the algo. So you have the data, you have the huge amount of data for the training set, then you can drive your learning. So the goal is that it's essentially, so the question is that then what is a good regularizer or what is a good regularizer in my optimization framework, right? Regularizer is essentially, you think of a regularizer in all this optimization, it's actually related to your model. For example, you want to come up with a solution which is sparse because I know my model is sparse, my data is sparse. But how do you know the data is sparse? So one interesting area is, can I actually learn from my data, drive my learning? It's an iterative method so that I can choose the best regularizer for the unknown model. So this is sort of related to big data processing, but you can think of, so it's a big data processing in the context of network and communication. One realistic application you can think of real-time and large-scale analytics. You want to do a lot of analytics real-time. For example, you have an autonomous vehicle. Everybody is riding autonomous vehicle. You can imagine the vehicle itself is actually running on the real-time analytics on the fly. The last area is a very interesting area. It's complicated. It's essentially a notion of network intelligence. The sense is essentially if our network itself, all the way from, let's say, transport layer, application layer, down to different stack of layer, you can think of the whole thing is essentially like a brain, right? So how do you actually design such a framework as if like our brain does, right? Each local function itself has some neural network. They operate very efficient manner, in energy efficient manner, and they are connected when it's needed. So sort of our vision of a future network. So then it is essentially very efficient. If not, if not the current way of applying directly a neural network into our network, you can foresee that it runs huge amount of data. It uses a huge amount of computing power, and it's not efficient. Complexity is a problem. Cost is a problem. Services is one, and you don't want the network to be like that, right? And I think that is sort of the drive, the vision of what 6G is, and sort of a service adaptation design. Okay, so this I think that covers a lot of very, very interesting areas. So I'll go into the second part of the talk, which is to actually exhibit some of these results that we have in the past few years. So I'm going to talk about the first one, which is deep learning for visible light communication. I just want to show what can be done in a very traditional type of problem. It's a sort of physical layer type of problem. So visible light communication is one type of channel. So information is conveyed through temporal intensity changes of the optical pulse, right? You switch LED, the LED on and off with different rate, where this is basically transmitted like 1001 and so on. So it's information. A lot of applications, a lot of vehicles now, in fact, a lot of cars has LED light, right? So you have LED light, you actually can communicate, right? So this is a very useful area, especially in our future cars, right? When car to car can communicate with each other. Visible light is one area. Underwater is another area to travel through the water. Hospital aircraft, because you don't want to use RF because of safety, because and a lot of indoor scenarios, let's say convention hall and so on, we have light. So light could be a way for you to transmit data. So the system model, you can think of, for simplicity, I'm going to look at on-off keying based PLC. I have a bit coming in encoding, and then so I have a sequence of symbol, an optical channel, I have a detector, I have a decoder. So in terms of the notation wise, I can implement this with a white LED, input message B from 1 to M, output binary code words of length N, so this is L log 2M. Here at N, I have a dimming constraint. So you can think of this like a power constraint. So how many of these symbols should be on and should be turned on, and how many should be turned off. So you look write this into a notation wise, I can actually write this into a simple system model. Y is equal to xb vector plus nth and sh. So this vector of noise, what is actually different? This is a thermal noise, sh is a short noise. Because of the nature of this optical model itself, right? So because the LED is turned on and off, so this creates a short noise. And short noise depending on the input, right? So that's why we have the input noise, which is a non-linear noise. So this is our system model. So what is our design goal, right? So the goal is to find an efficient encoding decoding strategies. For us, this is a very simple OOK based PLC model. Objective is to minimize the symbol error rate. So we see that, oh, this objective function is definitely non-convex, right? Symbol error rate usually is a complicated function under dimming constraint. So what I mean, you can think of this like power constraint. So if you think of code word, we're going to use a very simple or established code word. It's called a constant weight code. So all code words in CWC have the same Hamming weight. And this is well studied in the information theory community. The mathematical properties is well studied. We know that this code exists and for a specific code word, code rate, and the minimal Hamming distance. So unfortunately in the community, in the IT community, is that there's no results that show how do I actually do this optimal encoding method. So can I do it in a very efficient manner? And I will show that we actually can do it in a very efficient manner. So the whole idea is I do an end-to-end. So I'm going to propose an autoencoder framework. So this is B coming in. I'm going to do a encoding network, which replaces my transmitter. I have a receiver, which is a decoding network there. But what is actually different from the conventional autoencoder is that this is essentially, I actually have S that comes out, then I have the noise coming in before I goes back to my receiver network, right? So what is actually different? Because of this, there's caused a lot of issue because you know that my S are binary 1 0 1 0 0. So that caused an issue. So what is the fundamental issue? It's essentially, if I'm going to do a very simple binarization, because all neural networks there are real numbers. If I'm going to allow this simple binarization, right? If I just want to do a step function where depending on real number, I do a step function. The problem is that my gradient vanishes, right? If you have read up a bit on all this neural network, it requires backpropagation and it uses stochastic gradient descent. So the problem is that if the gradient vanishes, then everything stops, right? So it's essentially the algo is unable to find a better sort of a peak or a valley depending on your optimization problem. That is, find a better local optimal point. That means it suddenly stop, and it stop at a very bad point, which you don't want, right? You want the algo to keep on looking to find a better solution. So the idea is actually you can do a soft binarization. So I can do a parameterized signal activation function, which is tuned by delta. So if delta goes to infinity, then I have a step function, right? So this is my signal function. So the idea is that actually you can do a multi-stage training algo. So it's essentially in stage 1, I'm going to do a very smooth type of function. I know it doesn't really satisfy my constraint because my constraint, dimming constraint there, is requires all my S to be 1 and 0, right? But this is an initialization. So I'm going to do this, I'm going to do this initialization. It's a trained autoencoder. I'm going to initialize the second stage. I'm going to a multi-stage, right? So if I go to a multi-stage, then the purpose of this, you ensure your stochastic gradient algorithm is always moved to a better point. better initialization point until I think it's sufficiently good. So what I mean by sufficiently good is up to you to actually define. Then I'm going to output this as. So as an example, I can do a autoencoder delta as 1,000. You see that if I do a naive hard binarization, this is my result. But if I do this proposed multi-stage training, I actually improve quite a lot. And with that, we actually verified that optimal 7.7 is actually the paper from the information theory community, where this is the Hamming weight distance and this is the different code rate. We can actually achieve all the optimal value, the optimal Hamming distance. So this shows that our results work. Beyond that, what is actually different is that in the result in 7, it does not assume any of the short noise, right? It's just the AWGN. So by our neural network type of design, we actually can incorporate more than the thermal noise. We actually can have the short noise. And we see that actually it performs much better than most of the result, right? So optimal is optimal CWC, but they went through an exhaustive search, right? Then you can do a random type of random search for the code, but then I have my result. So in this first work is to show that actually such a framework can be used for designing a very sort of traditional type of communication type of model that we see y is equal to s plus n, except that now in order to show that I'm interested in applying into places that it's not just AWGN, because a lot of AWGN type of models, we know the sort of optimal way of doing things, optimal cohort. But if I have more complicated type of noise, then I think neural network all this will be an useful application. So the next book that I'm going to move to is called distributed learning. So I've mentioned about this distributed learning in when I talk about this future, some of these future topics. So I'm going to motivate by a very generic optimization problem, and I'm interested in non-convex, right? So in a lot of resource allocation type of problems, actually can formulate in the optimization problem, and you think of it. A lot of the problems are in practice. We are optimizing some function f, ax. A is some random variable. X is my optimizer that I'm looking for. I'm subjected to some constraint, another function g, where A is also random. Then X is all from my feasible set solution. And it's not just one constraint, up to k constraint. So a lot of times in our community, you see a lot of papers where, first of all, they don't talk about expectation. First of all, they'll look for functions that are nice so that they can use convex methods or have some characterizations of the optimization problem. But if you think of it, when you want to do in practice, let's say my A is fast fading, right? A. Let's say I look at this as an interference channel, where F is the capacity, sum rate capacity of all the interferer, all the users, and A is my channel. But in practice, it's going to be hard to actually run this, because I will not ever run this optimization problem in a millisecond, right? You want to run this, okay, I'm going to run this over average, right? Expected average. But then if I have this expected average, the problem is, okay, I will not be able to find a closed form solution, right? And that optimization have integral, we know that it's a continuous optimization, it's complicated. So we face a problem, right? That is, in practice, I want to have a problem like that, but it's too complicated to solve. So can I actually solve using a neural network approach? And can I do further than, can I do a distributed? And that's what I'm going to do. I'm going to give just a very explicit example. So if I have a distributed network, 3 node, right? Node 1, node 2, node 3. All the A's are local observations, is random variable. You can think of a channel state information. Each node, they want to find best X, which is the local solution. You can think of a resource allocation strategy. They want to find the best X, right? But this network is actually exchanging information, because they want to solve a problem which is minimize or maximize objective that incorporate that. together. So they're going to exchange information across a link, which I call a backhaul, 1 to 2 or 2 to 1, depending on something called a backhaul capacity, right? If backhaul capacity goes to infinite, means that information are exchanged from node 1 to node 2, which is the channel local observation, which is A1, A2, is perfect, right? It's full perfect. You don't actually quantize it. But then if I have finite capacity, I will need to quantize. I need to quantize in node red so that I can send a few bits over. So we know, oh, if you send a few bits over, then it's an issue with my optimization problem. So let's explicitly look at this from an optimization problem formulation. So I can formulate this as this similar problem that we see in the few slides ago, right? Expectation A, and I'm going to find optimizer, which is a function of my A. So if perfect global information, my X is actually equal to this function ZC over A, and possibly non-convex objective function, F is not convex, G is non-convex. It's not easy to tackle such a optimization problem. So this is centralized. So if I'm going to formulate the same problem with the distributed manner, just think of that in the plot figure there, where now I need to exchange my information across from node 1 to node 2. So V is my quantization. That means I need to quantize my my information exchange from one to another, and this is my how many levels I want to quantize, quantization level, right? So this is my backhaul constraint. So I'm going to solve this optimization problem. So I'm going to apply a deep learning approach. So you can think of deep learning approach is a way of approximating unknown functions, right? You have a lot of training data, you actually can approximate this by finding all the best weight. So, but the technical challenge of the problems P1 and P2 is that now I'm going to train this over a long-term constraint, right? Because of expectation. And I have a distributed version. And I need to do binarization, as you recall, because of my backhaul constraint. So how am I going to do it? So first of all, I need to map my conventional type of problem into a DNN formulation. That is, I'm going to replace all this complicated type of function optimization variable to a DNN parameter, right? So I'm going to find a parameter through a neural network, where now you can think of as a mapping of ZC now into this phi C. Okay, so I'm going to map this. I'm going to go use data to find. But the problem is now I have constraint. Right? So how am I going to tackle the constraint? First of all, I have the last constraint. The last constraint is actually a projection. It's a projection into a convex set. So you can imagine that the last constraint, which is a short-term constraint, there's a short-term constraint here, actually you can incorporate into the outer layer of my neural network, right? Because it's a convex projection. So we know that it can be realized by linear operation. The gradient is actually well-defined. So it can be trained with my backward propagation and my gradient descent. So everything is fine. So you can imagine my last constraint actually can incorporate it into my neural network of the DNN, right, PC. Right? So the problem in fact becomes just this, right? Because my last constraint is incorporated into my neural network. So this problem, one approach, of course, you can say I go to do the penalty training. I just bring out my constraint. I have another phi here where I can do another grid search over this parameter, hyperparameter, right? So this is called hyperparameter search. Of course, this hyperparameter, let's say I have a hyperparameter for different k, then of course it's a grid search. You just need it. But can I actually do more than that? Because this does not guarantee any feasibility, right, or any strong result. So I'm going to do from optimization approach where when we have such a problem, actually we can do a dual, right? I can do a Lagrangian dual problem, and we know that this approach has been done in many classic problems. I give an example that in 2000, more than 10 years ago, where they solved this non-convex spectrum optimization problem for multi-carrier or DMA. It's a non-convex problem, and the approach is using this Lagrange duality. Of course, that this result is much more interesting. Essentially, they show that by satisfying some property, which is time sharing property, the zero duality gap holds. That means the dual problem and the primal problem has a zero duality gap. So in this problem, of course, we don't have this zero duality gap unless the problem is convex. So, but I can write my Lagrangian, right? I can write my Lagrangian problem. I can formulate as a dual problem. By doing so, what's the advantage? Now, my algo is very efficient. I can do a primal dual update, which is very, very efficient, right? It's a very efficient. The DNA parameter and the dual variables are jointly updated by a single stochastic gradient descent rule. And this can be trained and can run very efficiently. And I can actually make this in a distributed manner. And likewise, so you've seen the primal and dual. So the difference for the P2 is essentially I just need to incorporate the non-binary constraint. So the binary constraint I can actually incorporate in the projection. Right? So that is if you're interested, you can look at the paper. But the key is actually can incorporate that into the neural network. Centralized training I can perform in an offline manner. Distributed learning I can train and implement at each node and compute. So I'm going to look at some of these results. So we look at the problem. It's a classic problem more than 10 years ago. It's a connective MAC problem. So I have a primary user, I have a secondary base station, right? So essentially, secondary want to use a primary spectrum and it causes interference to here. So the goal is that I want to ensure that I maximizes the sort of the capacity of such a the secondary network, and I want to minimize the interference I cause to the primary. And of course, this function is convex, so I know the optimal solution. I can write a closed form. But the goal is that since we know what this optimal, so I'm going to replace this by my neural network. So I run some simulation. Then in fact, the black lines is the optimal solution from the classic paper. But what we can extend is actually we can extend this with my neural network. Centralized solution, I can get exactly what they have, but I can actually do more than that. I can do beyond that in the distributor. I say that, okay, my channel information that I send that I need to exchange from the primary to secondary, the channel state information is imperfect. I need to quantize for different levels. So what's the gap I have? So this is the strength of the way it actually verifies that, okay, my framework is optimal if you give me a convex problem, but I can actually extend, I can incorporate backhaul constraint. So I'm going to look at, the goal is to look at something non-convex, where I know the popular solution to solve this problem is the weighted MMSE. It's not optimal, it's just a local optimal. Where we see that the blue line, the black solid line is the WMMSE, is a local optimal solution. But by using our approach, you can see that you actually can beat the WMMSE for a centralized case, where so we can actually find a way to have a better solution using such an approach. So, so we see that we have developed sort of a framework for looking at this constraint optimization problem for our community. But this is just one scenario. There's a lot of extension. If you can imagine that now, because I'm looking at such a very simple structure of a network, the question we have, can I go beyond such a structure, right? So it's relationship with message passing. Yeah, so relationship, can I do a different type of architecture? So then you will have to redesign your neural network architecture in a different manner. The last work I want to share is scheduling for federated learning. And this the motivation is a lot of the data is at the edge, whether it's handphone or your Google Home. Data is there, and you don't want to upload all your data to the cloud to do some application. So the notion of federated learning is, okay, I want to let the edge devices to do the state-of-the-art machine learning, and they just send their weight up, right? Their neural network weight. So they keep the raw data, is actually keep at the device. So I just do a training, on-device training, and everybody has a global model. Right. Of course, we know the more data you have, the model becomes better. So that's why all the edge node want to collect the train weight and to update the global model. So in terms of picture, you can think of this. They want to solve, for example, the global model wants to solve SVM, linear regression, or K-means. So this is a global optimization problem want to solve. But now each device, because the data is here, they're going to run a neural network, and they will essentially have this weight run on stochastic gradient descent and going to send to the agent, or you can think of the AP of fusion center. You're going to do a weighted average. So device perform local training, send the train weight to the aggregator will average the model, redistribute, and they go in a few rounds. If the link is perfect, what I mean is that the weight that is sent to the aggregator is, let's say, it's on a interference-free, noise-free type of channel, then this will converge. Okay, so the question we have is that, let's say I'm going to apply this into a wireless network context, right? And we know that the problem is that the channel is shared. The medium is shared because it's an important resource. Transmission are not reliable due to interference, due to noise. And only a limited number of devices will be selected. You can't have everybody sent, right? You will have to do scheduling. So the issue is how to schedule devices, update train rates, and how does interference affect the training. So you think of, again, create sort of a result that is, let's say I think of an access point, it could be a Wi-Fi AP, wants to do this federated learning, have these handphones, the data is there, then it will send the weight, right? I extend this into look at a big network, right? So my AP are all person randomly deployed or randomly deployed, and each AP has, let's say, K associated K user, right? In this cell has K user, the spectrum is divided, N is smaller than K. I'll do a global reuse. So the each UE or device in a cell will collaborative train on the same model, but the data is on the device itself. The device will download a global model. They perform local training. The access point will select N out of K because the spectrum, there's a limitation on the number of spectrum you have. So there's a few scheduling policies you can actually use. You can actually uniformly select N out of K, random, or you can actually group them into groups and sequentially select, or you can do proportional fast scheduling, right? Select the best N out of K, right? So there's a few scheduling, and you can have more different types of scheduling mechanisms. But when you apply this federated learning into the edge, so the measure is a bit different because the train update will only be successfully received by the AP if and only if, first of all, it has to be selected. Second off, once you selected, you of course send your weight up, and it can be successfully decoded because you're sent over a wireless link in a packet form. You must be able to decode. If not, you cannot have the weight itself. And the metric is the number of communication rounds to reach an epsilon accurate solution. So I'll not go into details. You can actually characterize the convergence. You can characterize the result, how many rounds you need for different scheduling mechanism. I'll just show some of these numerical results. First of all, when you have a very high threshold, right? Very high threshold, you can see that proportional fast scheduling is the best, right? Because once you have a very high link, I think of the way I can use millimeter wave, for example. I can ensure that I have a very high SNR because my beam is very sharp. I will reduce the number of interference. Then this type of technology, I can actually use this for learning. I can use this to update my weight very efficiently, right? However, in other cases where my SNR is not so good, then my scheduling mechanism is very simple. I can do a round-robin type of scheduling. So there's many type of extension of this work incorporate. For example, how do you incorporate latency? Can you incorporate the neural network into here to design a better scheduling mechanism? or how does the scheduling mechanism depending on your location or depending on your channel state information and so on. So there's many ways you can actually incorporate to make your scheduling more efficient. So the last few slides, I'm going to just share some other works that we have done, and you can actually, if you're interested, you can just take a look on the IEEE Explorer or in the archive. So a work that we've done many years back is actually, you can actually apply this in a sensor data. In the way things are do fusion, you can do heterogeneous type of fusion to design your neural network. You have different modalities. So this one way you can use neural network. You actually can apply some of this classification, right? Because machine learning is good for classification. I can actually do this for collision resolution by looking at different classes for MAC. For random access, how do I resolve in the case of massive connectivity? Can I use a neural network to help me to do that? Can I try to do neural network where my video cameras wants to do real-time edge analytics, where now my camera also has a small GPU, but of course you cannot run all the data set. You can run a small data set, but then because my camera itself is wirelessly connected to my backend server, so you don't want to send everything up. So you want to send something more important. So how do I actually define what even more important? I do some processing, some small neural network. So you can imagine I have a small neural network at the front end and something which is more sophisticated at the back end, and how these two can be combined. So it sort of goes back to all this wireless video transmission together with this neural network. How do you actually improve such a system? Today I actually didn't talk so much on the higher layer. One interesting area is this slicing, network slicing concept. We actually can do reconfigurable slicing. How do you define when to reconfigurable, what to reconfigurable, and can you do very fast slicing or slow slicing? This you actually can incorporate with a neural network, because a lot of all these problems are optimization problems. I'm going to conclude with my last slide, as I mentioned. So why is actually important to look at this? It's not to actually apply this into all the past problems, right? In this talk, the primary is to show that actually it can perform, at times perform better than some of the solutions, non-optimal solutions that we have done in the past. But what is actually important is actually to understand how this can be effectively used in our future systems. I just give you an example of 6G because of a lot of interest in 6G discussion starting from last year all around the world. The question we know is that it's going to be more complicated because 5G and beyond, we look at all the services applications coming in. So so you want to have a network which is sort of adaptive. You want it to be applied because you have different type of technologies you can use. So I thought AI, you have this intelligence, could be an efficient way to help me to, let's say, do my best resource allocation. So where to apply? This is one question we need to have. And when to apply, right? In the Notion, we think of the example that have random variables, right? There is a lot of applications or system we have requires knowledge of, let's say, location, knowledge of how good a particular channel is. And you see that a lot of all these random variables has a time scale, right? Depending on how fast things change, right? So we have to be very careful when we apply, because if you apply it in a system that changes so fast, you know that it's useless, right? Because after you learn it, things change. So when to apply is an important question, so that this sort of mechanism, this AI technique is robust. And how to apply, right? How to apply in a way that, how to apply, because you can think of, I can apply it, perform well with the expense of huge amount of complexity or power. And I don't want to do that. So you want to apply in an efficient manner, which is all related to cost of applying, right? Privacy is the issue, complexity, robustness, because you want to make sure that you don't want a system that applied, then it breaks down, security and trust. So you can think of it security, trust, robustness, complexity, all these are constraints. So once you add this constraint, so there's a lot of very interesting problems that we can arise. So many interesting questions do remain. So I think it's a good time to relook, and that's why we relook at some of the past problems to look at our things that we have done in the past. So our conventional wisdom, things that we learned in our university, things we learned from past top scientists around the world, top papers, but maybe it's time to relook some of the way things been done. Maybe it's no longer the best way, optimal way to do things, because things that by adding some of these issues, complexity, adding all these additional constraints in, and machine learning or AI is sort of the way to look at this to solve such a problem. And with this, I'm going to end my keynote speech. Thank you for your time, and thank you for listening. Thank you very much.
Hello everyone. I will demonstrate the Wavelet denoising algorithm for high-speed satellite communication. The demonstration is divided into 6 parts. First of all, I will compare the basic principles of Fourier transform and wavelet transform, so that we can understand what wavelet transform is faster. Then, explain Mallat algorithm. The third part describes the steps of wavelet threshold denoising. Fourthly, the relationship between the order NA and the decomposition level NDEC is discussed. Fifth, the introduction of common threshold function and the design of new threshold function. Finally, the application of wavelet threshold denoising in satellite communication is introduced. Next, I will present the first part of the demonstration. As we all know, Fourier transform is based on sinusoidal function, which approximates a function or signal with infinite length and variable frequency. The amplitude of sine function is the sparse representation of signal. In the same way, wavelet transform approximates the signal with the wavelet function which decays rapidly in the whole time domain. The average amplitude is 0, and the time frequency window is variable. The wavelet function decomposes the signal by the scale change in frequency and the shift in time, so as to get the sparse representation of the signal. Of course, no matter sine function or wavelet function, for the sudden change signal, because of its limited bandwidth, the reconstructed signal has ring, which is Gibbs phenomenon. Generally, for digital signal, binary discrete wavelet transform is used to decompose it. Like FFT, there is a fast wavelet transform algorithm, namely Mallat algorithm. Mallat algorithm uses a pair of quadrature mirror filters to decompose and reconstruct the signal. This processing process is similar to for filtering algorithm, but Mallat algorithm filters the signal in an iterative way, and the number of iterations is equal to the number of decomposition layers. Finally, the approximate coefficient and detail coefficient are obtained. Well, we already know Mallat algorithm, and wavelet threshold denoising is to insert a thresholding step between Mallat decomposition algorithm and Mallat reconstruction algorithm. That is, thresholding the decomposed detail coefficients and reconstructing them with approximate coefficients. Of course, before denoising, we need to determine the wavelet function and decomposition level NDEC. The commonly used wavelet functions are Dowbake's wavelet, Simlet wavelet and Coeflet wavelet. For the same kind of wavelet function, the higher its order is, the smoother the wavelet is. The more ideal the frequency domain response of the corresponding filter is, and the larger the filter coefficient is. Therefore, for the smoother signal, the wavelet function with higher order should be selected reasonably, and for the application with small amount of calculation, the wavelet function with smaller order should be selected. Generally speaking, if the number of decomposition levels is too small, a large amount of noise will be retained in the approximation coefficient. Because Gaussian noise is evenly distributed in the whole spectrum range, and a small number of decomposition levels means that the approximate signal has a large bandwidth, which can accommodate more noise. Similarly, if the decomposition level is too large, it means that the bandwidth of the approximate signal is small. If it is less than the bandwidth of the useful signal, some useful signals will enter the detail signal, which will be reduced or zero after threshold processing, which will lead to signal distortion. In order to clearly understand the influence of order NA and decomposition level NDEC of wavelet function on denoising effect, Table 1 is drawn. In Table 1, NA is the row variable and NDEC is the column variable. The signal-to-noise ratio is used to measure the denoising effect, and the SNA trend chart of each row and column is obtained. It can be seen that each order of wavelet function has an optimal decomposition level, and the optimal decomposition level is relatively concentrated, so the correlation between wavelet order and decomposition level is not very strong. These are three views of the three-dimensional graph drawn in Table 1. It can be clearly found that the signal-to-noise ratio oscillates with the wavelet order, which may be the mismatch between the scale of wavelet function of different orders and the scale of signal, and the phenomenon of signal-to-noise ratio oscillation with the order of wavelet. Therefore, the selection of wavelet order should also consider the matching of wavelet function scale and signal. The graph is the relationship between the number of samples n and the signal-to-noise ratio. It can be seen that the number of decomposition layers is related to the number of samples. The larger the number of samples, the greater the number of optimal decomposition layers, and the increase of the optimal signal-to-noise ratio, which is the result of oversampling. Next, threshold and threshold function. There are three common threshold functions: hard threshold, soft threshold and semi-soft threshold. But they are inflexible. They are not fine. According to the characteristics of the threshold, the appropriate function is selected to form the threshold function, which can take into account the principle of simple form and flexible adjustment. At the same time, it can approximate the other three threshold functions and achieve good denoising effect. In the high-speed satellite communication, the actual collected optical fiber signal not only contains random noise, but also has clipping distortion. After denoising by wavelet threshold, the noise level decreases and the truncation distortion is improved. After the spectral subtraction filter, the amplitude of partial signal decreases greatly, resulting in obvious distortion. After Wiener filter, the small amplitude part of the signal has obvious implication. The results show that the wavelet threshold denoising effect is better. Okay, my presentation is over.
It's my honor to give us this topic. My name is an off-grid sparse respiration based locational method for near-field sources. My chapter contains 5 parts. The first is introduction. The second is signal mode. The third is methods mentioned. The fourth is simulation experiment. The end is the conclusion. The introduction. In this paper, we propose an off-grid sparse respiration based locational method for near-field sources. This method established an off-grid signal mode based on angle parameters by obtaining high-order cumulative max and then realizes the estimation of angle by means of alternating interactive optimal methods. An off-grid signal mode both on distance parameter is established. The second part is a signal mode. Suppose there are k narrow band near-field signals incident on a new film linear array with n array elements. The index value of the array elements is omega is from m to m. As shown in the figure, the incident angle of the kth incident signal relative to the range narrow is theta k. If the middle array element is taken as the reference array element, the distance between the kth source and the reference array element is Rk. The second part is a method mentioned. In the method mentioned, there have 2 paths. The first is a solution of angle parameters. The supposed method contains of 2 steps. First, the first order cumulative max is obtained according to the array output information, and the angle-based off-letter signal mode is established to solve the angle information. Secondly, the off-grid signal mode based on distance parameter is established to realize the resolution of distance parameter. The first-order calculus mechanism is obtained according to the array output information. The angle-based off-letter signal mode is established to solve the angle information. The second part is the slope of the distance parameter. The off-grid signal mode based on distance parameter is established to realize the solution of the distance parameter. Before we introduce the method proposed in this paper, we propose the following hypotheses. First, in order to avoid angle amiability, the max interval d should satisfy d is less than the quarter of lambda. The second, the incident signal in error band 0 mean center knowing random process, and its first-order parameter is not 0. Error received signal is independent of the signal, and its active 0 means grass-wide sources. The first constant is a simulation experiment. In the first part, the simulation experiment is the changes of MRES with MR3 with the SNR. It can be seen from the figure 2. A, the off-grid signal method proposed in this paper can approach CRLB at a fast speed and continue to decline with the improvement of SNR and always keep close to CRLB. In contrast, although OSA can approach CRLB first, but its MRSE cannot continue to decrease with the increase of SNR, which shows a performance saturation phenomenon. OPMUSIS has low performance due to the loss of error imputation caused by the introduction of a smoothing method. TSMMUIS established similar estimation performance. It can be seen from figure 2b that the method in this paper is always close to CRLB when the SNR is greater than 45 dB. OPMUSIS can only approach CRLB while the NR is greater than 5 dB. OSA derived from CRLB even when the SNR always relatively high. TSMUIS, on the other hand, performed poorly. The simulation experiment of the two parts is the changes with the number of Quek bits. It can be seen from the figure 3a that the method in this paper can approach the CRLB while in the whole range of snapshots. TSMUIS shows similar estimated performance to the method in this paper. OPMUIS and OSA have underperformed. It can be seen from figure B that the method mentioned still provide excellent estimation capability in the aspect of distance estimation. OPMUSI performed similarly, while the other two methods performed less well. It can be seen from the above two simulation experiments that the method prepared in this paper has a stable and excellent near field sources location capability. The last part is a conclusion. This paper presents a location method for near field sources. Firstly, by operating a high-order cumulate matrix, we contrast an angle based off grid signal mode, and then employ the alternative interim optimism method to estimate the angles. Then, by taking advantage of the angle estimation information, the off-grid extension mode based on the distance parameter is contrasted, and the method similar to the angle estimation is used to obtain the distance estimation value. This method not only has high estimation accuracy, but also can realize the automatic pairing of angle and distance parameters. Thank you.
My presentation is Space-borne multifunctional integrated hardware processing platform design. There are 4 chapters. The first chapter is Introduction. The second chapter is Overall Design of New Hardware Platform. The third chapter is Performance Analysis of Platform. The fourth chapter is Conclusion. First, Introduction. With the development of microelectronics, computers, signal processing, and other technologies, as well as the wide application in the field of satellite communications, the requirements for multifunctional and universal hardware platform have increased significantly. The traditional hardware processing platform generally has the characteristics of specificity. It develops specific hardware platform for specific application scenarios, and its functions have been solidified to meet specific requirements. At the same time, when the functional requirements of users in orbit change, the product will not be replaced, and these problems have seriously restricted the development and application of the product. In order to solve these problems of satellite, traditional hardware platform, it is necessary to study a hardware architecture platform with versatility, flexibility, and freedom to upgrade. Secondly, it is necessary to build a high-performance digital signal processing platform that is suitable for a variety of needs. Third, the development of low power consumption, miniaturization, lightweight characteristics of hardware architecture. These requirements greatly heighten the implementation difficulty of the hardware platform. 2. Overall design of new hardware platform. Traditional hardware platform include ADC, DAC, FPGA, DSP, CPLD, peripheral, storage, and interface chips. The main problem is that area and power consumption will be increased sharply. The overall design of traditional hardware platform is as follows. This new Space-borne multifunctional integrated hardware platform includes RF SoC, DSP, DDR4, interface chips, and so on. The overall design of new platform is as follows. 2.1. Direct RF sampling design of new platform. The RF design signal are converted to IF signal by 1 or 2 analog down convention, which is traditional method. Then the IF signal is sampled by ADC. The traditional RF front requires a relatively complex design scheme with many discrete analog devices. Moreover, if the receiving frequency is variable and the bandwidth of filter can be set, the volume of system will be increased. In order to solve these problems, the new platform design in this paper adopts the direct RF sampling technology. It moves the AD and D as close to the antennae as possible. It has the advantages of less device required, low cost, low power consumption, and easy to obtain higher performances. It has great significance to the miniaturization, integration, and low power consumption of equipment. 2.2. High integration design of the platform. In this design, RF SoC has 16-channel transceiver. It is obviously that the new platform doesn't need an extra DC ARM controller and power conversion chips correspond to these devices. Therefore, it also reduces the difficulty of distributing the printed board and difficulty of dividing the power layer. RF SoC, the core chip of the whole processing platform, integrates processing system and programmable logic resources. The processing system includes application processing unit, APU, real-time processing unit, RTU, DDR controller, system controller, security module, platform management module, and various common interface management. Programmable logic resources include RF signal chain, common I/O, storage module, and DSP resources. The core idea of Space-borne multifunctional integration platform is to integrate IPG, ARM, and RF in sampling as much as possible. 2.3. Power module design of platform. The power supply of RF SoC is the most complex part of the processing system. As shown in the figure 4 below, there are as many as 14 power taps. The selection and design of power module is an important factor that restricts the size and weight of the platform. For decrease the volume of platform, inter-power modules are selected in this paper. 3. Performance analysis of platform. 3.1 Lightweight analysis of platform. The new platform already considered the module architecture, implementation of the different applications, and various interfaces. And the platform chooses higher integration, low power consumption, and storage processing capacity of the chip in order to support the establishment of lightweight. At the same time, in order to make the processing platform universal, RFSoC is selected. RFSoC integrates RF ADC, RF DAC, ARM, IPG, and high-speed interfaces. So the hardware platform is nearly half the size. The input RF frequency of RFSoC can reach 16 GHz. If the input RF frequency is below 6, the mixer oscillatory bandwidth is not needed. It greatly reduces the power consumption, size, and development cycle of entire system. 3.2 Low power consumption of platform. In the new platform, the power consumption of DSP is estimated at about 10 watt, and the core voltage of RFOC is 0.85 watts. The static current is less than 2.5 amp, and the static power consumption is less than 2.1 watt. When the program runs, the power consumption of RFSoC is less than 25. So the total power consumption is processing platform is less than 35. When the power conversion efficiency is 90%, the total power consumption is less than 40. 3.3 Reconfiguration of platform. RFSoC and DSP are the main components of a hardware platform, which can realize different functions by loading different programs. By storing different software packages and corresponding control instructions, users can switch processing tasks. The reconfigurable characteristics of the hardware platform are shown in the figure 5 below. The numerical control method can adjust the frequency band of filter, and the SPI control method can change the gain amplitude of the RF signal. Sampling clock and NCO clock are adjustable. The programmable logic devices and DSP devices are controlled by and configured by the control unit to realize the desired functions. Algorithmic programs with different processing flows can be configured according to applications. 3.4 Deep learning of platform. In this design, the RFSoC is used to implement the deep learning algorithm. Firstly, the selected neural network structure type and the deep learning framework are determined according to relevant tasks. Second, the network training is completed on the PC, so that the accuracy of the network meets the expected requirements. Third, the specific architecture of the deep learning module is determined, and the neural network API call is written by using high-level comprehensive tools. Fourth, neural network computing engine matching the trained deep neural network is constructed under RFSoC. Finally, the program running on the ARM within RFSoC is written to task the whole classifier. The overall architecture of deep learning module based on RFSoC is shown in Figure 6. 4. Conclusion. In this paper, a design scheme of space-borne multifunctional integration platform is presented. The platform has the ability of direct RF sampling and high-speed data processing. At the same time, the platform is characterized by low power consumption, small size, lightweight, and reconfiguration. It provides a new way to solve many problems of traditional hardware platform. Therefore, the design platform can be widely used in aerospace equipment, which can greatly reduce the hardware cost of the upgrade system and can improve the data processing capacity. Thank you.
Hello everyone, I'm delighted to report our research, multi-modem implementation method based on deep outcode network with you. In this paper, a 10-layer deep outcode network is designed, and 2-array to 64-array modem are implemented based on this 10-layer DAN. During this process, a unified loss function and a unified optimization algorithm are utilized to train and test the 10-layer DAN. Finally, the demodulation performance that is close to, consistent with, or better than that of traditional MPSK or QAM is obtained. The above-mentioned DAN and its training method provide a new way for waveform generation and reconstruction in intelligent communication satellites. 1. Introduction. Satellite communication has been more and more widely used due to its many advantages. However, there are many aspects that need to be resolved, such as signal function, difficulty in upgrading and maintaining, and weakly ability to adapt complex extramagnetic environments. On the other hand, artificial intelligence, represented by deep learning and reinforcement learning, is infiltrating or even subverting the traditional industry. In many fields, it has shown wisdom beyond the human brains. Therefore, combining artificial intelligence with satellite communication can effectively improve the performance and security of satellite communication systems. Similar technology. Adaptive code modulation as a technology that can achieve a good compromise between signal capacity and reliability between adjusting the coding rate and modulation order and different channel conditions has been widely used in wireless communication systems. However, this method usually needs to implement multiple coding and modulation with different odds and different rates separately, and then select a certain combination of coding and modulation to complete the combination according to the perception and decision of the channel environment. This will make the design, implementation, and hardware cost of the communication system multiply. The most similar to the research of this paper is reference 5 and reference 6. In these two papers, a different network structure was utilized for each group of N and K, which is not conducive to the efficient implementation and reconstruction of multi-code modulations. In addition, only I and Q signals can be transmitted over actual channels, while in these two papers, channels of data are transmitted directly, which bring about spatial diversity gain, thus obtains superior performance to the traditional encoding and modulation. Therefore, this cooperation is little far from reasonable. In view of the deficiency of above work, We focus on the realization of multi-modem based on a unified DAN architecture in hope of providing a new implementation method for intelligent and efficient waveform generation and reconstruction for satellite communication systems, and improving the anti-interceptability of the waveform. First, a 10-layer DAN is designed, and based on this 10-layer DAN, 2-array to 64-array modems are realized with a unified deep learning network architecture, a unified loss function, and a unified optimization algorithm. The parameters of each layer and the optimization training method are given. Second, for each of 2-array to 64-array modem, the modulation constellation symbol mapping relationship, network convergence speed, and performance comparison with traditional demodulation methods are simulated. 2. Multi-modem model based on DAN. This is a 10-layer DAN we designed to implement multi-modem. It is mainly composed of a compression E-code for modulation at the sending end, a decompression decode for demodulation at the receiving end, a optimization goal which minimizes the loss function, and a optimization algorithm for updating or trainable parameters. The compression E-code consists of an encode input layer, 500 layers, and a 2-node output layer. After the output T, the noise is added into the transmit signal. The structure of parameter setting of the decompression decode for demodulation are completely symmetrical with the compression E-code for modulation. The estimate of transmitted symbol are obtained by looking for the index of the maximum value in the node of output layer, and then the bit error rate can be obtained. In the 10-layer DAN, sigmoid activation function and tangent activation function are used. The output of the sending end is as this function. The output of the receiving end is as this function. The optimization objective is as this function, and the optimization algorithm is as this function. 3. Training and test verification. First, the methods we train our model as follows. We use small random numbers to initialize the parameters of our model. The training set includes 4,000 random integers ranging from 0 to n-1. We select 7 dB, 12 dB, and 13 dB as the training SNR for 16 array and its below, 32 array and 64 array modem respectively, and we select 10,000 rounds, 20,000 rounds, and 30,000 rounds for 16 array and its below, 32 array and 64 array modem respectively. Small bench training, with each bench include 1,000 symbols, is selected as our training method. Learning rate, attenuation coefficient, and the minimum constant, which present the denomination from being rather when updating gradient, are set to 0.2, 0.95, and 10 to the power of minus 8. The test set includes 100,000 symbols random numbers from 0 to n-1. Finally, TensorFlow and signal CPU are selected as our training environment, it takes about 5 to 8 seconds totally for 200 rounds. Second, training and test results of multi-modem based on DAN as follows. Figure 2 and Figure 3 display the constellation diagram, coding constellation, demodulation performance are consistent with BPSK and QPSK respectively. In Figure 5 and Figure 6, we can find that the constellation diagram and coding constellation are different from 16QAM and 32QAM, and their demodulation performance are close to but slightly worse than 16QAM and 32QAM respectively. In Figure 4 and Figure 7, we can find that the constellation diagram and the coding constellation are different from 8QAM and 64QAM, and their demodulation performance are close to but slightly better than 8QAM and 64QAM respectively. For 128 array, we find that the 10-layer DAN cannot distinguish its constellations and its demodulation performance deteriorated seriously. But when we extend the 10-layer DAN to 12 layers, with 18 dB training SNR and 40,000 training rounds, the demodulation performance better than 128 QAM can be obtained. In order to show the training parameters and performance of the 10-layer DAN for multi-DAN more obviously, a summary is presented in Table 1. This result shows that the 10-layer DAN can only complete modem of 64 array and below. For modem of 128 array and above, a deep network structure and more optimization parameters are required. Furthermore, we can find that the constellation features of 8-array modem and its above are very different from traditional QAM and difficult to distinguish linearly. So, the multi-modem based on DAN can improve the anti-interception capability of satellite communication. The problem to point out is that it is also obvious display in Figure 2 to Figure 9. With the increasing of modem orders, the training round is increasing remarkably, and their convergence rate are become slow accordingly. 4. Conclusion. In this paper, a 10-layer of DAN is designed to realize modems from 2-array to 64-array with a unified network architecture, a unified loss function and a unified optimization algorithm, and the demodulation performance that is close to, consistent with, or better than that of traditional MPSK or QAM are obtained, which provide a new way for intelligent generation and reconstruction of satellite communication waveform, and improve the anti-interception capability simultaneously. In addition, the 10-layer DAN network has the ability to be flexibly extended to accommodate higher-order modems. Our further tests show that the multi-modem model based on DAN can adapt it to multi-path environment and effectively suppress narrow-band interference by adding a convolutional layer at the receiving end. Further research directions include overall learning and training of coding and modulation based on a deep learning network, generation of modem with specified frequency dominant constraints, signal synchronization at the receiving end, and intelligent interference detection and suppression ethic. Thank you for your attention. Please leave your comments and advice about the report. We will make further improvements according to your feedback.
Hello everyone, I'm the keynote speaker of this report. My name is Renwei Wu. I'm a lecturer in Changchun University of Science and Technology. My topic today is inter-satellite link assignment based on reinforcement learning. Next, I will introduce our research in the following 6 parts. First, we will introduce the background of our research. Multi-satellite cooperative network have gradually become an alternative solution for future space missions. The key to realize the multi-dimensional cooperative network is to build inter-satellite link. There are many advantages of inter-satellite link. It's very suitable for level constellation, which is not convenient for global station building. Moreover, constellation with inter-satellite link has very strong invulnerability. Inter-satellite link can expand the coverage of constellation communication without the ground station. However, inter-satellite link has its own shortcomings. The available microwave spectrum resources of inter-satellite link are fixed and limited. The antenna and the laser terminal of inter-satellite link is difficult to capture, track, and aim. The space-time variation of satellite link makes the network topology, optimization, and routing selection extremely complex. Inter-satellite link assignment is the basis of constellation networking technology, and the communication performance of inter-satellite link largely depends on the assignment of the inter-satellite link. The ground network topology generally does not change much in a long period of time, while the inter-satellite link topology will change with time due to the influence of satellite motion. Therefore, it is necessary to conduct special research on inter-satellite link assignment to solve the problem of dynamic change of link topology. Chang et al. Divided the period of the level satellite system into equal time intervals by using the idea of the finite automata. In each interval, the inter-satellite visibility was not limited, and the topology of the inter-satellite link remained unchanged. The follow-up studies had basically adopted this idea. An effective inter-satellite link assignment schema is to improve the overall or spatial performance of network on the basis considering the service requirements. Focusing on this problem, a lot of representative research has been completed, which can be divided into 3 categories according to different solutions. First, the link assignment problem is constructed as the optimal combination problem. Real conditions of satellites are mapped into various constraints. Performance indicators are set as the optimization objectives. The link assignment problem is modeled as a Second, the link assignment problem is modeled as a special search problem, and the graph search method is used to search the optimal solution. Third, the idea of divide and conquer is adopted to solve the problem of link assignment. Because of time, we will not describe them one by one. In our research, reinforcement learning is used to solve the link assessment problem. The link assessment problem is modeled as the optimization of the link selection action sequence. This modeling can provide a new solution to link assignment. In our research, a link assignment based on reinforcement learning is proposed for the first time. The interaction model between link selection action and the environment is established. By selecting the actions of the inter-satellite links by agents, the rewards related to objectives are obtained, and the link assignment is optimized by accumulating the multi-rewards. Here, we will introduce the concept used in our research. Satellite constellations are suitable for demanding link topology, but satellite link capture time is long enough that frequent link switching will lead to a decrease in the overall performance of the network. As a result, satellite constellation link need a time-sharing plan. Based on this idea, Chang et al. Adopted the idea of a finite automata, divided the circles of the low-orbit satellite system into equal length intervals, and maintained the inter-satellite visibility and changed during interval. Dong et al. Inherited this idea and divided the constellation system circles into FSAs with a duration of the TFSA. Our research is also based on this idea. The link circle table should be established by the conventions that inter-satellite visibility is unchanged. The following are the commonly used mathematical symbols and their representation. Constraint can be divided into three categories: inter-satellite visibility constraint, connectivity constraint, link number constraint. In the process of optimization, link combinations that violate the above constraint cannot occur. Satellite system has highly sensitivity to link delay, so the main optimization goal of our research is the delay performance of the whole network. The topology generation of the link is transformed into two delay optimization problems. Two delay index are the average delay of network and the maximum delay. Next, we will introduce the main ideas of our method. In the application of the reinforcement learning, two problems need to be solved: the definition of the action and the design of action utility function. We can decompose an action of selection combination into multiple consecutive actions of selection parts of the combination. That is, select the part of the combination first, and then select a part from the remaining combination, and continue to select until all parts of the combination are selected. In this way, each action of selecting will have an impact on subsequent actions of selecting. There are two variables that affect the action utility: the average delay and the maximum delay of networks. two goals may not be achieved at the same time. It is an inefficient scheme to realize the link topology traversal by selecting link combination. Here we can adopt an equivalent scheme. We assume that the link topology is fixed, and we can realize the link topology traversal by changing the position of the satellites, which is not only reduce the operation of the selecting actions, but also realize link topology traversal equivalently. Our algorithm will be introduced in detail below. We use a special data structure to store the value of each action utility. We call it Q. Here is a brief introduction of the data structure Q. As shown in the figure, is a tree-like data structure. Let us assume that there's capital N satellites. Capital N equals to k multiplied by lowercase n, and from which lowercase n satellites are selected. There are a capital N lowercase n possibilities for this action of selecting lowercase n satellites. In the same way, there are a capital N subtract lowercase n possibilities for the next action of selecting lowercase n satellites. The similar selection will continue to perform the k subtract 1 times until each satellite is traversed. And when all satellites are selected, the satellite sequence will be generated. According to this sequence, the corresponding length combinations can be generated. The average delay and the maximum delay can be calculated respectively based on the link cost in matrix C, and then the action utility value of the selecting satellites is also calculated. The variable mean is used to point to the action of the minimum action utility value in the next possible action. It can reduce the number of times to traverse the whole data structure. The flow of algorithm is as follows. Because of time, we cannot explain them one by one. Our simulated result will be introduced in detail below. It can be divided into 4 parts. The first part is optimizing model. Figure 4 shows the delay comparison. The link number is 3 and the satellite number is 8. Figure 5 shows the delay comparison when link number is 4 and the satellite number is 8. By comparing figure 4 and figure 5, we can see that the number of links increase from 3 to 4. The average delay and the maximum delay decreased. This is because the increase of the links brings more low delay links and more possibilities of the link topology. The link assignment algorithm can find the link topology with low delay. Therefore, both delay performance are improved. In addition, when number of the link increased from 3 to 4, the number of the iterations increased. This is because the increase of the links lead to the increase of the calculation. The second part is generating optimal link topology. Figure 8 shows 3 different link topologies. When link number is 3 and the satellite number is 12, figure 8 is the initial link topology. The initial link topology can be manually set in the first FSA state, or it can be the previous link topology retained in the previous intervals. Figure 8 B is a static topology. When the link number is 3, each satellite has 3 fixed links in the static link topology, 2 of which are respectively established with the 2 adjacent satellites in the same orbit, and the one of which established with the 1 adjacent phase satellite in different orbit. Figure 8c is the link topology generated by the optimal algorithm. The third part is the link changes in different topology. Figure 9 shows the number of the link changes from the initial topology to optimized topology. It can be seen the increase of the link and the increase of the satellites will affect the number of the link changes. When the number of the link increases from 3 to 4, it leads to the increase of the link changes. When the number of the satellites is 8, the number of the link changes is 18. When the number of the satellites is 12, the number of the link changes is 29. When the number of satellites increases from 8 to 12, it also leads to the increase of the link changes. When the number of the links is 3, the number of the link changes is 29. And when the number of links is 4, the number of the changed link is 29. Figure 10 shows the number of link changes from the static topology to optimized topology. We can get a conclusion similar to Figure 9, that is, increase of link and satellites will affect the number of the link changes, and both positively related. By comparing Figure 9 and Figure 10, it can be seen the number of the link changes in the static topology is more than the number of the link changes in initial topology. This may be due to the large gap between the static topology and the optimal topology. It can be seen that the link topology switching is frequent and the static topology is not suitable for inter-satellite network. The first part is performance comparison in case of disruption. Figure 11 shows the effect of the link disruption on delay. Specifically, one link is interrupted at the 0th interval. 2 links are interrupted at the 30th interval. 3 links are interrupted at the 60th interval, and all interrupt links are recovered at the 90th interval. The delay performance is simulated when satellite number is 12 and the link number is 3. The simulation results show that the optimal topology has better delay performance compared with the initial topology. The maximum delay and the average delay are lower, and the delay variance is also small. Finally, we summarize our research. The proposed method is an attempt to solve the link assignment by reinforcement learning, but there are still many deficiencies. It mainly focuses on 2 aspects. One is to use the idea of the Q-learning to solve the problem, but the scales of the Q-learning will greatly increase with the expansion of the problem scales, which will affect the optimization results. The second is that the number of the satellites and the link in the simulation is too small to meet the simulation requirement of the large number of the satellites and the links in level constellation. The future work is focused on 2 aspects. One is to improve the reinforcement learning model. I'll try other reinforcement learning model for more complex optimization. The second is to increase the number of the satellites and the links in the simulation and improve it closer to the real level environment.
Hello everyone. Now I will introduce our paper. The topic of our paper is Research on Intelligent Transmission of Space-based Information. These contents will be introduced. First, I will introduce the background of our paper. In our work, the space-based information merely refers to the data captured by satellite platforms. These kinds of information are mainly from the ground or the air targets and stored in various forms for transmission to users. With the rapid development of space-based technologies, there are more and more satellites in outer space, including the remote sensing satellite, the imaging satellite, the communication satellite, the navigating satellite. As a result, the amount of the space-based data will increase exponentially. A large amount of space-based data needs to be transmitted from satellites to ground, which brings high requirements for the capacity of the satellite-ground data transmission link. The increased demand of the transmission capacity will take up more frequency resources, but scheduled frequency resources limit the improvement of the satellite ground data transmission capacity. In addition, the increasing number of satellites on a bit may also cause frequency interference to neighbor receivers, including not only the natural interference and the man-made interference, but also the malicious interference that may come from a hostile attacker. Therefore, the contradiction between the data throughput demand of the space-based information and the transmission reliability of the satellite ground data link becomes more and more serious. How to effectively avoid the interference spectrum, improve the reliability of satellite ground data link, and maximize the use of the limited and valuable frequency resources need to be solved urgently. According to the development of related techniques, there are three aspects deserves attention. First, in recent years, satellite communication technology has developed rapidly towards a direction of high throughput and high reliability. Second, the software-defined satellite becomes a new developing trend through software-defined radio, software-defined payloads, software-defined data processing computers, software-defined networks, and other means. Different function modules of a satellite can be realized based on software. Third, intelligent spectrum radio technology continues attracting attention of the research field. We know that the cognitive radio has been proposed by Dr. Mitora since 1999. It is considered as a kind of radio that dynamically changes its parameters based on interactions with the external environment. The cognitive radio is an intelligent wireless communication system which can use artificial intelligence techniques to learn from the radio environment. By changing the transmitting frequency, modulation, and coding mode, transmission power, and other working parameters, it can adapt to the change of wireless signal statistics, achieve highly reliable communication at any time and any place, and effectively use the spectrum resources. Two basic abilities of cognitive radio are the cognitive and reconfigurable abilities. Then, based on the above analysis, combining the cognitive radio with the space-based data transmission technique, and using theories and methods of artificial intelligence, we introduce an intelligent data transmission strategy. It will have the ability to learn, recognize, and predict the spectrum environment, and then adaptively select the parameters and working methods to avoid interference spectrum more effectively. Such an intelligent data transmission technique may effectively improve the communication performance. Intelligent intelligent transmission of space-based information integrates the electromagnetic environment perception, the interference detection and identification, and dynamic spectrum allocation, the adaptive parameter configuration, and the intelligent decision engine into the conventional data transmission technique. A brief system spectral diagram is shown in this figure. First, by establishing a cognitive model of the electromagnetic environment, the interference spectrum identification can be realized at the ground receiving station. Second, based on effective cases stored in the cognitive knowledge database, the intelligent decision engine dynamically determines the optimal transmission frequency bands using the reasoning and optimization methods in artificial intelligence, and adapts the transmission parameters to reconstruct the transmission waveform. Finally, the communication parameters shall be updated synchronously with the satellite through some signaling parameter transmission channel, and then the satellite carries out a new period of data communication based on its reconfigurable transmission platform. The interference spectrum identification and the channel prediction module shall be optimized by continuously accumulate the spectrum sensing data and employing machine learning methods. On the one hand, it can avoid the interference spectrum. On the other hand, it can achieve the efficient use of available spectrum resources. To realize the aforementioned intelligent data transmission system with reconfigurable parameters, it is necessary for the satellite's data transmission platform to be designed with a software-defined architecture, as shown in this figure. In a space system, the data transmission platforms of satellites for different applications should be uniformly designed based on software communication architecture. This kind of data transmission platform has such abilities, including reconfigurable broadband RF front end, so that the radio frequency part of the transmission platform covers a wide frequency band. Second, software-defined computing unit, so that the satellite can realize onboard spectrum sensing and interference identification. Third, software-defined parameters managing unit, so that the satellite can change communication parameters as required. The last one is software-defined storage unit, so that the satellite can efficiently allocate storage resources according to different tasks. There are several key issues to realize the intelligent data transmission technique. The first one is the spectrum sensing and cognition. This is the foundation of the cognitive ability of the system. It mainly involves modeling, detection, recognition, and prediction of the interference signals. Common methods include engine value decomposition, cyclic spectrum detection, and energy detection. To classify and identify the interference, we need to extract the features of the interference signals first. Then, we can further use pattern recognition techniques to design a classifier, including support vector machine, extreme learning machine, and artificial neural network. Since the historical spectrum data contains the laws and the characteristics of the spectrum environment, machine learning-based methods are widely used. Related methods can be divided into three categories: supervised, unsupervised, and reinforcement learning. Two representative methods based on reinforcement learning are Q-learning and deep reinforcement learning. Deep reinforcement learning uses a deep neural network to approximate the Q-value table in the Q-learning algorithm. Due to its strong generalization ability to deep neural network, the deep reinforcement learning method is easier to mimic the internal laws of the spectrum environment. The second one is the design of the intelligent decision engine. The decision engine uses a decision-making optimization methods to give optimal decision according to the historical experience and certain constraints, and then generates system parameters and constructs the link waveform according to the decision rules. The learning and reasoning algorithm is the core algorithm for the decision engine. The genetic algorithm, reinforcement learning, case-based reasoning, and neural network can be used. It is an effective way to design the intelligent decision engine based on the case-based reasoning method. At this time, it needs the ability to store, analyze, and make use of historical experience. The cognitive knowledge database is a critical part. Through continuous communication tests, the cases in the database are constantly updated. Then the whole decision engine is continuously optimized and updated to adapt to the changing spectrum environment. The structure and organization of the knowledge database directly affects the response speed and execution efficiency of the decision engine. So it is very important to design a proper structure of the database. The next one is massive data processing. The proposed intelligent transmission technique needs to get a larger amount of spectrum data so as to facilitate the intelligent decision engine to make decisions on the optimal communication parameters. The data to be processed can be divided into two parts. The first is the spectrum sensing data, and the second is the cases data for decision making. The main problem of massive data processing is to discover the laws of the data and mine the hidden information in the data. More attention should be paid to the deep learning based data mining method and the computational intelligence based distributed optimization method. In addition, how to take into account the real-time performance of the system as well as ensuring the effectiveness is another key issue. One potential way is to build a supercomputing center on the ground, develop the combination of cloud computing and edge computing, and make full use of various computing resources of the whole system. The last one is the reliable satellite ground signaling parameters synchronization. Different from the conventional parameter fixed data transmission architecture, an important change is the need for signal parameters interaction between both sides of the communication link. When the communication parameters are not suitable for the current spectrum environment, it is necessary to send the new parameters to the transmitter and the receiver before applying new parameters. Reliable parameters transmission can be realized by designing a special channel. And this channel should need low transmission rate but high reliability and concealment and anti-interference performance. As we can see from the above introduction, the intelligent space-based data transmission technique is very complex and but it really has potential advantages in interference spectrum avoidance and efficient utilization of the space spectrum resources. We know that there are still many key issues need to be well studied, and this the remaining problems need to be solved. From a developing perspective, in our future work, we may focus on these two issues. The first one is the space-borne reconfigurable transmission platform. The second one is the reliable satellite ground signaling parameter synchronization mechanism design. The reason why we choose these two issues is that other aforementioned key issues have been more or less investigated by related scholars, but these two issues are more challenging and valuable. We think that if these two issues can be solved effectively, then the intelligent space data transmission technique may go to realization. Thank you very much.
Hello everyone, I'm Xiangyin Wei. It's a great honor for me to present our work, Edge Computing Empowered Satellite-Territorial Networks, Service Architecture, Use Case, and Open Issues, on behalf of my colleagues at NUDT. This is the outline of my presentation today. First, I will give a short introduction of our work. AI and satellite networks are expected to be an essential part of the sixth generation communications due to its unique advantages like a wide coverage area and easy to establish lateral-side communication links between a satellite and the ground devices. And the communication of satellites are hard to be affected by the bad weathers, and the broadcast nature could enable a satellite to communicate with a large number of devices at the same time. However, current satellites are usually fixed and closed designed. It means they couldn't flexibly reconfigured on demand, and their functions are determined at the first design. Last but not least, they are usually very expensive. Recently, several satellite projects are announced by the big companies, such as Starlink by SpaceX. It has launched more than 500 satellites so far, and Amazon has announced a project named Cooper, and it will launch more than 3,000 satellites in the next 10 years. In China, a smarter satellite named Tianzhi has launched by the CIS with embedded neural network processing capability. And Aerospace Corporation has tested Space Cloud, which aims to move the cloud into the aerospace. The overall objectives of the future satellite service should be a smart service with embedded deep learning capability, and it could be reconfigured on the fly and can provide a flexible on-demand service. Edge computing is another new paradigm which aims to bring computation, storage, and communication resources to the network edge, and enabling source and data processing and response. It could be a great enabler for realizing intelligent or smart satellites, enabling satellite-based intelligent service through moving edge computing facilities onto the satellite, and it can bring the following advantages, like processing data in the space, remarkably reduce the latency, and it could enhance the security of the data processing process, and decrease the transmitted data volume. This is very important for the satellite service. However, move cloud onto the satellites is a non-trivial task due to 3 reasons. First, the payload of a satellite is usually very limited compared with a server at the territorial cloud data center. Second, the common tight coupling design of the satellite payloads is not flexible enough. Third, the high mobility nature of satellites limits the service time of each satellite for a particular area. So, for the edge computing empowered Satellite-Territorial networks, SDN, we need to first devise a service architecture for the edge computing empowered SDN. First, we need to clearly state the service provision process. Third, we will provide 2 inspired use cases. And last, we will discuss the open issues in design and implementation of edge computing empowered SDN. This is our edge computing empowered SDN service architecture. It contains 2 pools, that is the resource pool and the service pool. And in these 2 pools, we design 5 layers. The bottom layer is the physical resource layer, as the blue frame enclosed. And then comes the virtualized resource layer. The third layer is the basic service layer. Then is the service composition layer. The uppermost layer is the service access layer. Let me first introduce the resource pool. It is further divided into 2 layers. The physical resource layer is in the bottom. It contains all the physical resources in the SDNs, like sensors equipped on satellites, vehicles, mobile devices, and IoT devices. The computation facilities located on satellite edge computing facilities, vehicle computation platforms, and the cloud data center. The storage disks installed on aerospace and ground platforms. Last one are the transmission devices and links between diverse networked platforms. Using virtualization techniques, these resources can be virtualized by the virtualized resource layer. In this layer, we divided all the physical resources into different kinds of service resources. The first one is the sensor pool. It contains all the available sensors. And the second one is the transmission pool. It contains all the switching, routing, transmission, devices, links, and protocols. The third one is the storage disks, all available in the system. The last one contains all the computation facilities and the algorithms running on these devices. This figure shows the details of the service pool. The service pool is divided into 3 layers. The bottom layer is the basic service layer. It is in charge of providing basic services that typically have simple functions like image analysis based on convolutional neural networks, text-speech analysis, based on recurrent neural networks, content caching based on popularity-aware algorithms, task scheduling, spectrum analysis, messenger delivery, resource management, and so on. Through the service bus, it can support the service composition layer. This layer provides complicated functions that can be provided by many basic services like Earth observation, navigation, remote sensing, etc. And the upmost layer is the service access layer. This layer provides interfaces to the end-user devices. With a service manager center, they are in charge of service registration, service request, and so on. This figure shows the service provision process. When user initiates service request to the service access layer, its request will be directed to the service access interface, then to the service register center to check whether the requested service is available. If it is available, it will direct it to the service management center. After that, it will further deliver to the service composition layer and basic service layer, because a request may require many different services to collaboratively provide service to the user. And the service composition layer may call the basic services between itself and the basic service layer. On these two layers, the requested service will be resolved to different kinds of resources. After resource calculation, the resource request will be initiated by these two layers to the virtualized resource layer. And these layers usually providing sensing, transmission, storage, and computation resources. Then all the virtualized resources will be mapped to the physical resource layer. They will be provided by all diverse requested resources that are available in the STNs, like payload, network, and computation resources. In this layer, some reconfiguration may be happened on satellites, and the network could also be reconfigured by NFV or SDN technicals. So in this manner, the end-user requests will be delivered and mapped to the underlying resource layers. Then I will introduce two use cases. In the first use case, one single satellite is used as the transmission relay between planes and the ground station. The planes are deployed in the task area, and each plane is in charge of monitoring some particular area. And it is equipped with cameras that can take videos. For each video frame, it will deliver from the plane to the ISAT. The satellite can process the video frames using neural networks like video compression, video encryption, and then the processed video will be delivered to a ground station. And one satellite can serve many planes at the same time, and it can use other technicals to process different videos delivered by different planes to reduce the data volume transmitted between it and the ground station, as shown in this figure. And in the second use case, many satellites need to collaborate with each other to conduct spectrum sensing in a particular task area. In this use case, different satellites are in charge of sensing different spectrum bands. ISAT-1, ISAT-2, ISAT-3 can complete this task collaboratively. Then they will need to send the sensing results or data back to the ground station for processing. ISAT-4 acts as the transmission relay between ISAT-1, 2, and 3 to the ground station. In this scenario, all satellites will just sense the data and deliver the raw data back to the ground station through ISAT-4. We call it the raw data back scenario. In this scenario, we can also introduce intelligence onto the satellite. It means after the sensed data are collected by the satellites, they will first process the data and to reduce the data volume transmitted from the satellites to the ground station. They can use cluster analysis, neural networks, and machine learning techniques to conduct this task. Then, the sensing results will deliver back through ISAT-4 to the ground station. And we call this scenario sensing results back scenario. Also, the satellites don't have enough computation capacity to process all the data, so they can process part of the data and deliver the results back. It will be called partial results back scenario. And we can compare different strategies' performance. We evaluate them using numerical tests. And the latency of raw data back, partial data back, and sensing results back are calculated using this formula. And different form parameters are adopted to compare the performance. More details can be referred to our paper. These two figures shows the latency experienced by 3 different strategies with different raw data size and inter-satellite bandwidth. We can see that through introducing intelligence on the satellites, we could reduce the latency experienced by the spectrum sensing task. And these two figures also shows the latencies with the various processing frequency of a satellite and the cloud. We can see that when the processing frequency at the cloud servers are very high, we can just transmit the raw data back. It will not incur more latency than the sensing results back strategy. Several open issues still exist when we want to implement our service architecture. First is reconfigurable payloads design on the satellites. Second is the lightweight edge computing platform design. The third one is the heterogeneous network convergence. Fourth one is the security issues introduced by the open architecture. Last one is the resource cognition and scheduling. In this paper, we present a service architecture of edge computing empowered STNs, and is composed of 2 pools and 5 layers. Then each layer's function and the service provision process is detailed. 2 use cases are provided with numerical results, and 5 open issues are discussed. Okay, that's it. Thanks for listening, and questions can be delivered to our email. Thanks.
Dear everyone, I will introduce my paper, which is titled A Practical Joint Coding-Modulation Mode and Frequency Time Resource Allocation Approach in MF-TDMA Satellite Communication Systems. I will introduce my paper in 6 parts. First one is abstract. The second one is the introduction. The third one is the mathematical formulation. The fourth part is the time slot calculation. And the fifth part is the time slot allocation. And the final part is simulation. Now, I will introduce my first part, abstract. In general, the problem of resource management in MF-TDMA satellite communication system can be divided into 2 phases: a time slot calculation phase for each connection request, and a time allocation phase in frame structure. In this paper, we propose algorithms to solve these 2-phase problems. In the former phase, we first allocate each connection request on an appropriate carrier based on traffic demand of each connection request. And next, dynamically adjust the coding and modulation mode of each connection request according to the channel condition and the state of the system usage. Then we calculate the number of time slots requested to be assigned to each connection request. In the later phase, we propose an algorithm called best fit modified to allocate the time slots in the MF-TDMA frame structure. Simulation results show that although the total traffic demand generated by all the connection requests are various, the time slots is sufficiently utility due to the dynamical adjustment of the coding and modulation mode. However, the performance of the proposed BF modified algorithm is better than that of the existing algorithm. Now we will introduce the second part, introduction. This figure shows the configuration of MF-TDMA satellite communication system. There are several terminals and 1 network control center in the system, and each terminal provides service to multiple connections. such as telephone, fax, IP data, and so on. In this paper, the transponder in the satellite is assumed to be transparent. This MF-TDMA is employed as the Assignement method for both up and downlink. In addition, the terminal in the system supports multiple coding and modulation mode. In every frame, the terminal sends a connection request to NCC via the satellite, and then the NCC generates terminal burst timeline table and sends it to terminal. Upon receiving the TP-TP table, each terminal reads the TP-TP table to know what time slices are assigned. This figure shows the frame structure of MF-TDMA satellite communication systems. The frame is divided into carriers in terms of frequency, and each carrier is divided into time slots in terms of time. Each time slot consists of header, traffic, and tail. The header consists of several symbols which are used for bit synchronization. The tail is a period of free time, which is used for time slot protection. The traffic is time, in which the terminal sends information. The length of each time slot in different carrier is same or different, and different time slots can adapt different coding and modulation modes. This is flexible for us to manage resource. However, that introduces great difficulty to find the optimal solution for the resource management. To this end, in this paper, we aim to find a considerable solution to the problem. In the management problem, there are some basic strategies to obey. The first one is that a single terminal can't be assigned more than the total time slots in a carrier. 2. A slot can't be assigned to multiple users. 3. The set of time slots used by a terminal must be the same carrier. 4. The set of time slots used by a terminal to a given single connection must be contiguous in one carrier. 5. A terminal can't use time slots in different carriers that overlap the time. Now, we will introduce the third part, mathematical formulation. Based on the acknowledgement, we formulate the resource management in the MF-TDMA satellite system as follows. It is noted that the optimization problem is a nonlinear integer programming with constraint, which is NP-hard. NP-hard programs mean that the problem can't be solved in polynomial time. To solve the problem in a given time, we divided the problem into two phases. The first phase is time slot calculation, and the second is time slot allocation. Now, we first introduce time slot calculation. For the problem of time slot calculation, it is seen that the number of time slots assigned to each connection request is determined by the carrier sample rate and coding and modulation mode assigned to it. Here, we dispose the problem of time calculation into two sub-problems: carrier assignment and Coding-Modulation mode assignment. The step of carrier assignment is as follows. The main idea of the algorithm is that a connection request with higher traffic demand will assign on a higher seamless carrier. The period for connection transmit data will be smaller. The coding and modulation mode assignment algorithm is as follows. At the beginning of the proposed algorithm, each connection request is assigned to the lowest order coding and modulation mode in order to save the transmitting power of the terminal. If the sum of time slots assigned to all the connection requests is bigger than the total time slots of the carrier, then the connection request with the biggest link margin is chosen to adapt the one order higher coding and modulation mode, which is the most possible to support the higher coding and modulation mode. Therefore, the algorithm obtains a compromise between the transmitting power of each terminal and the system capacity. The algorithm for time slot allocation is as follows. In the algorithm, the carrier, which has the longest free time means that the time hasn't been allocated to any connection request, is prepared to allocate the time slots to connection request. If there are no free time slots or all connection requests have been allocated in the frame structure, then the algorithm is terminated. Now we will introduce the 6-part simulation. Now we will show the simulation result. First, we will show the efficiency of the dynamical adjustment of coding and modulation mode. In this figure, the mode 1 presents BPSK and mode 6 presents 16 APSK. It is seen that for the same number of the connection requests, when the mean value of the traffic demand is larger, the occupation rate of mode 6 is higher. It means that when the traffic demand is higher, the bandwidth efficiency of coding and modulation mode adopted by each connection request is higher. For the same reason, when the mean value of the traffic demand is same, the number of connection requests is more. The bandwidth efficiency of coding and modulation mode adapted by each connection request is higher. These 3 figures show the comparison of EIRP, time slot utility rate, and traffic rejection rate for the 3 approaches of coding and modulation mode assignment. It is seen that when the traffic demand generated by all the connection requests are low, the approach of maximum mode doesn't utility the time slot efficiently, causing a waste of bandwidth and unnecessary increase of power. On the contrary, the time slot utility of approach of minimum mode is almost 100%, regardless of the total traffic demand. However, since the number of time slots which should be assigned to each connection request is high, traffic rejection rate of this approach is the highest one among the three approaches. To overcome the drawbacks of the two approaches of maximum and minimum mode, the approach of dynamic adjustment modes obtain a compromise between total transparent power and system capacity. This figure shows the time slot utility rate in terms of the number of connection requests. It is seen that the proposed BF modified algorithm reduced the confusion caused by the restriction 5. The time slot utility rate of the proposed algorithm is higher than that of CF algorithms. This figure shows the traffic refuse rate in terms of the number of connection requests. It is shown that the traffic refuse rate of the proposed BF modified algorithm is less than that of CSF algorithms. That's all. Thanks.
Hello everyone, it's my honor to share my work, a model-driven development framework for satellite on-board software with you. My name is Qin Junxiang. This is the contents of my report, and now I will introduce the background and the related works. At present, commercial aerospace is developing rapidly, and a series large-scale constellations have been proposed and under construction. The most prominent is Musk's Starlink project, which is to build the largest constellation in history, with 42,000 satellites. On the other hand, through the development of satellite systems such as GPS, FLIO-FS, and so on, are also developing towards the following trends. The number of satellites has increased dramatically, and there is an increasing demand for satellite mission diversity and inter-satellite resource sharing. In the context of such industry development, people have increasingly significant requirements for the function, reusable, and rapid development of satellite software. But the traditional satellite development methods have such problems: poor software portability, local reuse rate, and poor development automation. The reasons may be, but not limited to, lack of standard development, backward development mode, and so it needs a kind of new satellite architecture, new development mode. According to the above-mentioned demand for satellites, some new systems have been proposed, such as CubeSat, plug-and-play satellite, software-defined satellites, and even SmartSat. By summarizing the character of these satellites, we find that they are also innovating the software, hardware, or development methods of the satellite. This satellite system's architecture changes from traditional to software-defined and to module and layer software architecture. With that change, the development process of satellite software development methods also innovated from structured development approach to objective-oriented to design pattern based on software architecture. And now, modern driver is the main trait. Typical satellite tools we will also investigate these tools, such as the Gen1 FSDK, CFSK, Scale, and MOS3. They are focused on some aspects and all have their own characteristics. For example, the Gen1 FSDK is focused on graphical development and stimulation, but CFSK has a functions of visual command and control, which is a useful management function for satellites. Take FSDK and CFSK as examples. They are both more advanced software development tools that appear in recent years, and they both improve the efficiency and reusability of satellite software and also introduce modern design. However, they support a limited number of hardware and software platforms. For example, CFSKs can only support the development of a limited number of small satellites and CubeSat software systems. Therefore, similar software development tools are so many and varied, but none of them have high versatility. To solve these problems in satellite on-board software development, we propose the framework that adopts unified architecture, standardized components, and configurable integration and automatical generation. Now, I will introduce the modern driver system framework. At present, modern driver software development methods have been widely used in many fields, but it is not for the strength that we use it, but for the reason that it can solve the problem and it meets the demands that the software development meets the demand of platform independent and function customized goals. This picture shows the relationship between the PIN and PSN. PIN means platform independent model. PSN means platform specific model. PIN helps to realize platform independent development, and PSN is matches with the platform through the modern mapping. And the picture shows the relationship between the model and the code. The tools connect the documents, models, and codes to the system design and realize automated verification of each stage of the development. The modern driver on-board software development architecture is a modern-centric software engineering approach. We know that satellite on-board software is extremely complex, but through graphical modeling, it constructed to capture the hierarchical hierarchical structure of the system and association between the layers, which is shown in the picture. By designing the model, automated developer and convert tools that shows in the left picture, the automated design can be realized. Here shows the design tool that based on the assignment model. The design tool completes the design, packaging and reuse software components, and establish a reusable software component library, and through automatic code generation can improve development speed. This is the flow of the on-board software development. In the step of the software component design, the developer will design a platform-independent model for on-board software based on the system component library. In the step of system parameter configuration, the platform-independent model will be mapped to a specific hardware platform and characterized in order to convert into a platform-specific model. After the configuration, the model will be transferred to generate the code. After compiling and testing, the code can run on the hardware device and becomes an app. All these development processes are iterated through the model, which can realize the standardization and automation of the development process. Now, I introduce the development tool tree, which is called STT. We made our design control, and here shows the overall design of the development tool tree. The tool tree consists of the software component tool, the system configuration tool, and the system text tool, integrated by a plug-in platform. The software component tool provides a graphical modeling environment. It can design software components and can build system software models according to the on-board software meta models. The system configuration tool can build the satellite hardware system model, establish a relationship with the related software component, and configure parameter. The software text tool can simulate satellite operations according to the integrated SDK kernel and realize the test of the software. In order to promote the development of the tool tree and improve the convenience of the data interaction between tools, the tool tree adopts a unified Sparse plug-in development platform. The platform is divided into 3 layers, and the tools we design is in the application development platform layer. A satellite mental model is used to describe the common elements of software component model. Although there is no uniform standardized architecture For onboard software now, we design the onboard software mental model. The software components are divided into atomic component and composition component SC, and they are modeled by UML. The picture shows the atomic SC and its design detail. Composition SC is used for presentation of the top-level system. It can control several atomic SC and composition SC supports connecting. So you can see that besides the connector and port, it contains the atomic SC. Here is the UML realized detail of the composition SC mental model. The system configuration tool confirms the correctness of the model by checking the constraints between the mental model. Then, by reading the hardware topology design file, the software components and the hardware are mapped, and finally the code is automatically generated, realize the transformation from PIM to PSN, just mentioned above. Now I will introduce the experiment. The development tool tray platform is shown in the picture. Besides the toolbar, project view, drawing board, the key part is the component design that is relied on the graphical editing. The graphical editing area is the area where graphs are created, active, and displayed. Other views provide some functions for the component editor, such as providing outline views, proper views, and so on. We use the I-Set1 to do the experiment. The I-Satellite-1 used two MCUs as power control and ball control. The two are connected by I-Fancy bus. It also used a J-Line SoC as the process of the SDR payload. The payload and the one OPC are connected via SNAP. A case is shown in the picture, which demonstrates the development process of the two tray platform. The case is about SDR system model. After the SDR system model is built in the graphical editing area, and the internet algorithm is designed based on the principle of velocity template engine. The second phase of target language compilation is carried out. With the software component description file and the hardware platform description file, the system configuration tool generates .c and .h code. Finally, the target file is compiled. The executable file can download to the target board and test its function. This is the process comparison between the traditional satellite development method and the modern driven development model proposal in this article. Through a modern driven approaches, connecting to the entire development process can effectively reduce manual code development, thus reduce the development time consuming, improve software reuse rate, can improve code quality, and so on. Finally, we can conclude what we done. We proposed a model-driven framework and designed settlement models of atomic components and composition components. Also, we realized a development tool tray and used the IC1 to test our flavor. That's all. Thank you.
Dear Chairman, ladies and gentlemen, good morning. I am very glad to have this opportunity to attend the WiSATS conference and to participate, listen, and share the innovative ideas with the top researchers. Let me introduce myself. My name is Zhixi Yang, and I am an assistant professor at the Academy of Military Science, China. The paper I'm presenting today is Approximate computing-based, low-power image processing architecture for intelligent satellites. The outline of my talk is as follows. First, the introduction for our research, including the background. Second, the motivation of our research, which would cover the main challenges. Then the major part of the talk, that is design methodology for the proposed design, followed by the fourth part, the results and the evaluation, and at last, some conclusions we have got. Firstly, I would like to introduce the background of the research. In recent years, approximate computing has been regarded as a promising paradigm for error-resilient systems to trade off the accuracy for better performance. Such systems include multiple medium processing, image processing, or the machine learning algorithms. The inaccurate results are generated by intentionally manipulating the arithmetic components, such as multipliers and adders. Approximate computing is a lightweight technique for image processing and could be transferred and used to the onboard processing within the satellite. In the perspective of the hardware, the multipliers and adders are the fundamental components for the DSPs and take up the major resources. The previous approximate design techniques include, for the multipliers, redesigning the fundamental components during the partial product reduction, and those components include the compressors, the adders, or the boost decoder. And recently, there are some new progresses as shown in the figures. References by selecting segmented inputs, eliminating the successive partial product errors, and so on. And for the adders, simplify the mirror adder at the transit level. There are several image processing applications using approximate components. For example, the left figure showed the approximate mirror adder-based the DCT and IDCT image compression application. The right figure showed the approximate multiplier-based image sharpening application. So from the results we can see, as shown in the left figure, the approximate adder-based DCT and IDCT application still has a good quality for the image processing. The key demands of the approximate image processing system should be lightweight. This requires that for the basic components, such as the multipliers or the adders, they should be with reduced power and complexity. Based on the preliminary analysis, here comes the motivation part. The first challenge is to design low complexity and a flexible accuracy adder at the transistor level. We could use the multiplexers to provide flexible results, but the traditional CMOS-based multiplexer is very complex. And the second challenge is to design variable accuracy multiplier. For the error-based multipliers, they are hard to adjust the accuracy, so alternative scheme of the multipliers should be used. Let's see the design methodology part. In this paper, multiplexer-based approximate adder designs are proposed, and the multiplexer designs use transmission gates, TG in short, due to the low power consumption than the conventional CMOS-based multiplexer. The figure here shows the accurate transmission gate-based full adder. It is the accurate adder, which has 3 blocks. The left XOR to generate the internal signals, the upper right XOR to generate the sum signal, and the lower right part to generate the Cout or the carry-out signal. By removing certain blocks from the accurate adder and reassigning the inputs to generate the output signals, several approximate designs are then available. According to the truth table on the accurate adder, there are 6 cases when the sum signal is the inverted Cout signal. So we can simply keep the Cout as accurate and use the inverter of the Cout to generate the sum signal. Then we can have the first approximate adder design in this paper, APA1 in short, as shown in the figure. In order to reduce the carrier propagation delay, we simply use the carry-in signal, that is the C-in, directly at the Cout signal by removing the upper right XOR from the accurate adder. So here shows the schematic of the second approximate adder, the APA2 in short. For approximate multipliers, instead of using error-based type, we use recursive multiplier. The recursive multiplier splits the inputs into 2 parts and performs the small bit width multiplications instead of using long bit width multiplication. According to different accuracy configurations of the blocks, we could obtain the variable accuracy multiplier designs. The newly proposed designs in this paper are the M4 to M6, and we used the previously proposed compressors for the blocks only. Okay, now we move to the results and the evaluation part. First, we compare the newly proposed recursive multiplier with the accurate multiplier. Both accuracy and electrical performance are investigated. The proposed approximate multipliers are simulated for an 8x8 recursive multiplication, with only the AH and BH blocks use accurate compressors, while the other blocks use approximate compressors. And from the results, as shown in the table, for M6, it had the best performance in terms of power, delay, and area. We also performed an overall comparison among the other previous designs as indicated in the references. And from a comprehensive view, M6 is a Pareto optimal design, which had the best trade-off in terms of both accuracy and the resources. The resources are defined as the power, delay, and area product. Comparison with approximate mirror adders is also presented for the single APAs in this paper in terms of the accuracy, power, and delay. Simulation is performed using the Cadence UltraSim simulator in the STM65nm process, for which 1.0 volt is used as the standard supply voltage. A load of 4 standard inverters is utilized, but its energy consumption is uncounted for the evaluation. The inputs are provided by independent voltage sources. Because some inputs drive the outputs, the energy provided by the input signals is also included in the simulation results. A comparison of each approximate design and the accurate full adder is pursued with respect to the power consumption, delay, and power delay product, PDP in short. All possible 16/4 transitions for different input combinations are considered for power and delay measurements. The delay is calculated from the input C-in to the output C-out, since it would propagate within a ripple carrier adder, and the value is the largest value among the 16/4 transitions. In terms of the power, the APA2 had the least power. AMA3 has the least value of the power within the AMAs, but the AMA3 has a larger MED or NED than the APA2, which means that the AMA3 has a poor accuracy compared to the APA2. In terms of the delay, because the APA2 is using the input as the output, so the carry-in to carry-out delay is considered to be 0. And for AMA1 to AMA3, they have similar delay, within which AMA1 has the largest delay, and APA1 has the largest delay as more than 0.2 nanoseconds. In terms of the PDP, which is the product of the delay and power, surprisingly, APA2 has the least value at 0, so the reason is obvious that the carry-in and carry-out delay is 0, so there is no carrier chain for the APA2. Well, for the AMAs, AMA4 has the least value. So in a general conclusion, AMA4 is a better design within the AMAs with acceptable accuracy and power consumption, delay, and the area. In this paper, the image sharpening is implemented as a real case study. The figure showed its implementation. For an approximate multiplier-based architecture, only approximate multiplication is used in the implementation. The left figure shows the processed sample images. The compressed image quality is measured by the peak signal noise ratio, the PSR. When compared to the accurate results, all the approximate designs, except the multiplier of the reference 2, produce images whose quality to gradation is not processed by the human eyes. The images generated by the multiplier of the reference 2 show the areas of low quality, indicated by the bold circles. And for M4, for the example images, the PSR is infinite, meaning that there are no errors for M4 for the processed example images. The table also gives the PSR values for these two images. All approximate multipliers achieve the PSR value higher than 30 dB. The PSRs of the output images generated by the M2, M3, and M4 and M6 reaches above 47 dB. This is a very high value that is acceptable by the most applications. The proposed design in this manual script showed a better image quality in terms of PSR value than the two reference designs of reference 1 and reference 2. For an approximate adder-based case, the addition is performed by the approximate adders proposed in this paper, while for the other operations like the multiplication, subtraction, and division, they all use accurate operations. The 16-bit approximate adder is used, where the lower 8 least significant bit use approximate adders, while the higher most significant bits use accurate adders. The table shows the PSR value for the sample image. They both have a good image quality with the PSR value above the 40 dB. Now we come to the last part, the conclusion. In this work, recursively based approximate multipliers and the two transmission gate-based approximate adders are proposed, and the proposed designs have better overall performance compared to the accurate and other approximate designs. The above proposed designs achieve lower power and a faster processing speed than the traditional image processing architecture, which could be potentially used in the onboard within the intelligent satellite as lightweight image processing modules. And this is all for my presentation. Thank you.
Good morning, everyone. On behalf of Wang Wei, I would like to thank you for this great honor to share our thoughts with you regarding the design and implementation of Global Navigation Satellite System Remote Docking Test Platform. My presentation will be divided into the following 6 parts. The first part, introduction. The second, architecture of the test platform. The third, process of platform operation. Next, key techniques. Then, implementation of the test platform. The last, conclusions. The first part is a brief introduction. The Global Navigation Satellite System includes satellites of multiple types, ground facilities with multiple functions, and various user terminals. To demonstrate the pre-designed schemes and protocol algorithms for the satellite navigation systems, supporting simulation systems are usually required. Some supporting simulation systems have been developed for the major satellite navigation systems in the world, such as GPS simulation system, satellite navigation software toolbox, Giant software developed by the United States, and Galileo system simulation software, Galileo system testbed, developed by the European Union. GNSS will carry out the satellite ground docking test in the initial and normal stages of satellite development. The major department of the GNSS project will develop their own devices and move their devices to the satellite plant to conduct docking tests for specific functions. The content of the test mainly includes: first, verify the status between the interface of systems. Second, verify the procedures of the information transmission and processing between the major systems. Third, check the performance for the realization of key indicators. This docking mode is incomplete, which cannot represent the true state of the system. Besides, it cannot verify system-level functions such as inter-satellite links and autonomous navigation. As a result, it takes a lot of time to carry out on-orbit tests after the satellite is launched. Our task includes building a system-level simulation system for satellite navigation system, which is multi-level flexible and can approximately represent the real state of the GNSS. In addition, the interconnection between the simulation task system and the real engineering system is achieved by the remote optical fiber. The presented simulation system can carry out the design verification of the system scheme, business processes, key technologies, inter-system interfaces, indicators, signal flows, information flows, and time flows under the state of the whole satellite navigation system. Using our simulation system can improve the docking efficiency, save the docking cost, and promote the implementation of high-density networking for satellites. Now, I will introduce the architecture of the test platform. This picture shows the composition of the remote docking test platform. It includes the space section, ground control section, and user terminal, which represent the technical status of the project. To operate with the above subsystems and improve the test scheme, the environment segment simulation subsystem, control and comprehensive support subsystem, global system simulation software, performance evaluation software, and information management system software are also inserted. The remote optical fiber system is added for connecting satellite plant signals to the simulation system. The space section represents the technical status of the GNSS, has the functions of satellite payload and platform control. It has the ability to pass commands from the ground control section. It is capable of inter-satellite data transmission and measurement, integrity monitoring, and autonomous operation. The ground control section forms a ground operation control network composed of a main control station, an injection station, and a monitoring station, and realizes inter-system interfaces and business processes. It has functions such as navigation business processing, operation management and control, satellite-to-ground data transmission and measurement, etc. The user terminal subsystem represents the technical status of typical application terminals. It has functions such as navigation and positioning, timing, and speed measurement based on the global system's downlink navigation signals. The environmental segment analog subsystem is connected to the space section, the ground control section, and the user terminal subsystem in a matrix of multiple inputs and multiple outputs. Is responsible for multiple satellites and stations on the ground. The radio frequency signals between multiple users and between satellites are superimposed with various dynamic characteristics, such as various relative motions, transmission channels, environmental effects. It converts static signals into dynamic signals. The control and comprehensive support subsystem realizes the unified monitoring and scheduling of test verification tasks and the operation service support for completing test tasks. It has functions such as power supply and distribution guarantee, reference time frequency signal, channel delay calibration, communication network construction, test task management, and test data processing and analysis. The global system simulation software completes the modeling, integration, and simulation tests of the core system of the global system in the form of software. It conducts comprehensive integration verification and evaluation of key algorithms. Performance evaluation software evaluates system service performance based on test data. The information management system software manages information such as files, data, and task records of the entire system. Thirdly, I'm going to talk about the process of platform operation. As a full-scale equivalent simulation system of GNSS, the test platform can operate independently, carry out simulation research and design verification of the core technology system. It can carry out comprehensive task verification of system operation control and interface between systems, confirm the technical status of the system, and support project construction. On the other hand, the satellites to be tested and the ground test verification system are interconnected through the remote optical fiber and the radio frequency signal transmission technology. The satellites to be tested in the test platform can be equivalent to one set of space segment satellite simulators, which are interchangeable with each other. Together with other subsystems in the test platform, the GNSS equivalent simulation verification system is formed to carry out a multi-satellite, multi-station, system-level integrated docking test involving multiple real satellites. Part 4 and 5 are particularly concerned about key techniques of the test platform. Let's focus on management of comprehensive control first. The test platform is a large-scale test system. Therefore, it has very high requirements for the comprehensive control. It is realized by the control and comprehensive support subsystem, which including 4 parts. First, the time-frequency subsystem is responsible for generating high-precision 10 MHz, 1 PPS, B-code, NTP, and other signals, providing a unified standard time and frequency signal for the entire test platform. Second, the test calibration status subsystem. It is mainly used for high-precision equipment time delay calibration of equipment. Third, the software and communication subsystem is responsible for the management control, business processing, data processing, and system monitoring of the test platform. Fourth, the power supply and distribution network subsystem. It provides a safe, reliable, and continuous power supply capability for the entire ground test verification system equipment. Among them, how to realize the high-precision time reference and time synchronization of the test platform, and provide the test platform with high precision, high performance, and high stability time frequency signals is the key to the operation of the test platform. The time base of the test platform is controlled by the time and frequency subsystem. This subsystem is controlled by atomic clock, reference signal distribution equipment, time and frequency distribution equipment, time frequency interface, satellite ground clock difference automatic measurement equipment, and GNSS time traceability equipment. Pictured in this slide shows the working principle of the time frequency subsystem. There is a more detailed explanation in the paper. Let's switch to the next key technique, which is transmission of remote interconnection. The GNSS satellite to be launched and the test verification system are distributed in different locations. The time and frequency reference is unified to realize remote interconnection transmission. Its principle is shown in this figure. The system includes sampling and recovery equipment in the master and slave computer room, transmission lines, atomic clocks, satellite common view receivers, and antennas in the master and slave computer room. The transmitting side uses the analog to the digital converter of the sampling recovery device to convert the analog RF signal to be transmitted into a digital signal and transmits it in the long-distance data line. The receiving side uses the digital to analog converter of the sampling recovery device to restore the digital signal to an analog RF signal to realize the long-distance transmission. The 10 MHz and 1 PPS signals output by both ends are synchronized by the satellite common view method. The sampling recovery equipment at both ends uses the 10 MHz and 1 PPS output from the satellite common view receiver at their own reference clocks to maintain the consistency of the master and slave clock frequencies. Due to the influence of the routing path, the transmission delay of the remote optical fiber fluctuates, so the data buffer is needed at the receiving end to remove the uncertainty of the data arrival time. The schematic diagram is shown in these two figures. The next part is about the implementation of the test platform. The GNSS Remote Docking Test Platform builds a multi-level flexible and controllable simulation test platform that approximately represents the real state of the GNSS. It can carry out simulation design and test verification that integrates all elements and the whole system. The test platform mainly has the following capabilities. First, it represents the overall technical status of the GNSS, and its composition and scale match the GNSS. Second, it has flexible and controllable system architecture. It also takes into account the mutually complementary verification methods of hardware verification and software simulation. Third, it has the ability to connect the satellites to be tested in the satellite plan to the system, and can carry out the ground integration test of satellite navigation equipment. Based on this platform, some tests were carried out. We verified the following performance: the correctness of the interface protocol between the satellite and the ground control section, the matching, coordination, and service performance of the integrated operation process of the satellite ground, onboard autonomous integrity monitoring functions, short message function and process, satellite-based augmentation information calculation, broadcasting and user receiving functions and process, autonomous navigation function and process accuracy. And in the process of docking test, we found related problems such as autonomous navigation and basic integrity of the two networks. This table shows the test result of the integrated operation performance of the satellite ground. Process of the satellite autonomous integrity is tested and verified. The figure shows the continuity of carrier phase and satellite clock frequency jump. In conclusion, the GNSS Remote Docking Test Platform builds a full-system, full-scale satellite navigation test verification system. It can provide 4 working modes: software, hardware collaboration, and virtual real combination. And it integrates design verification, engineering docking, equivalent operation, and simulation tests are all in one. At the same time, through the remote transmission technology of radio frequency signals, the satellite to be tested distributed in different locations and the ground simulation system are interconnected. A comprehensive docking test for parallel access of multiple real systems is carried out, which can effectively verify the correctness of the system level, service signal flow, information flow, and time flow for satellite navigation system, inter-satellite links, and autonomous navigation. This platform can fully expose the problem before the satellite is launched in order to reduce the risk and save the cost, and improve the construction quality of the project. This platform facilitates the implementation of satellite high-density networking launches. This is the end of my presentation. Thank you for your attention.
Hello everybody, It's a great time to attend the conference and give a presentation in this special form. The topic of my report is a method for performance evaluation of the low Earth orbit satellite networks. I will introduce our work from these 5 sections. With a deep exploration of space, an increasing number of low Earth orbit satellites have been launched for weather forecast, environment monitoring, communication, and so on. Especially communication satellite constellations such as Starlink and OneWeb require a large number of satellites, and it is important to evaluate the network performance of these systems. However, the large number of satellites bring difficulties in evaluating the performance of system. The general method is to use simulation software to run, such as OpenNet, NS2, NS3, and STK. But these platforms bring the problems of high time cost and high computation cost, and may not effectively reflect the actual performance of the network. We all know that the maximum flow algorithm can be used to calculate throughput or bandwidth allocation. But this method cannot evaluate the effect of the delay at the same time. Therefore, we propose a minimum delay maximum capacity algorithm based on the minimum cost maximum flow algorithm to obtain the bandwidth and delay of the network. First, we need to analyze the whole constellation of LEO satellites. There are several common configurations of satellite constellation, such as work dirt and work star. We focus on work star constellation. We can see the constellation elements in the table 1. It consists of N-orbit planes. M satellites are evenly distributed in each plane. The orbits are all circles with the same altitude, and the inclination of each plane is near 90 degrees. The phase offset is given by Formula 1. Next, let's build a satellite network model. Each satellite serves as a node in the network topology. The link between the satellite is the inter-satellite link, and between the satellite and the user is user data link. Each satellite has a maximum of 4 point-to-point LSLs. 2 of them are intraplane, and the others are interplane. ASLs over polar regions and across reverse seam are closed. Finally, we build a satellite network topology. In Figure 2, we can see the state of ASLs and seam. Finally, in order to describe the satellite network by program, we need to build a graph model. We can use the time-evolving graph to show the dynamic changes of the satellite networks. In Figure 3, within an orbit period, time can be equally divided into k time intervals, and the satellite network topology can also be divided into k different snapshots with the same time. The MDMC algorithm can analyze the network with single source and single terminal. while the satellite network is multi-source and multi-terminal. So we need to add a virtual source and destination. For example, in Figure 4, we build a work star constellation with 3 planes and 4 satellites of per plane. At the same time, we add 2 ground users numbered 13 and 14 as a source and destination to connect to the satellite randomly. Now we get a satellite network graph. When we consider the delay of a traditional network, we can use Formula 2. The processing delay between any 2 nodes is determined by specific hardware platform. When the hardware platform is determined, its value can be assumed fixed. The propagation delay between node I and node J is given by Formula 3. The cleaning delay depends on the specific traffic demand and the node processing capability, and it isn't considered in our method. So the total delay between 2 adjacent nodes is corrected to Formula 4. Capacity is defined as bandwidth or throughput between any 2 nodes, and the capacity is divided into 2 categories. One is generated by the all ISLs. The capacity of ISL is the same. The other one is from all the satellite ground links, which is from satellite to source or sink node. The capacity of the SGLs is regarded as infinite. In this section, we need to build a satellite network graph by program. In each snapshot, the step 1, we use the feature of satellite to build a network topology with the capacity and cost. Step 2, we add 2 virtual nodes as source and destination. In step 3, we calculate the visibility and the distance between any 2 satellites. Obtain the adjacency matrix and the delay matrix. Finally, in step 4, we combine them into capacity and the delay expansion graph. Next, we implement the MDMC on the topology we just built. The MDMC, based on MCMF, aims to calculate the minimum delay and the maximum capacity from source node to sink node. For example, in Figure 5, the source is node 1 and the destination is node 6. The solution of the MCMF is highlighted by red arcs. In the MCMF, the total minimum cost is given by Formula 5. The object is that finding a path from the source to the destination, which minimums the cost under the condition of maximum flow. In MDMC, the result is the minimum bandwidth delay product, which is the minimum number of bits with maximum throughput from source to destination. Then the minimum delay is given by Formula 6. For a given digraph with delay and capacity, in step 1, we construct a residual network by adding 1 inverted edge to every edge. Next step, we use the improved Dijkstra algorithm to find the minimum delay path from source node to sink node in the residual network. In step 3, we calculate the floor in this path. We add floor to positive edge and subtract floor from inverted edge, continuing operating the above steps until there is no path from source node to sink node. Last step, we get maximum throughput and the minimum BDP. Finally, we use the above formula to get the minimum delay. In the simulation, we design 3 cases. In the first case, we design and test 2 groups. The first group contains 7 constellations. The number of planes is set as 6, while the number of satellites of each plane is increased from 12 to 24. The second group also has 7 constellations. The number of satellites in each plane is set as 12, while the number of planes is from 6 to 12. Other parameters are the same in both 2 groups. In figure 6, we calculate the capacity and the delay of each constellation by MDMC from the 2 sets of the results. As the total number of satellites increases, the capacity of both 2 groups also increase, but the delay of the most constellation decreases. Then we compare 2 sets of the results. When the total number of satellites is the same, the capacity of FNSP is higher than FNOP. However, the difference between delay is much bigger than the difference between capacity. In conclusion, as the total number of satellites increase, it is better to increase the number of satellites in each plane than to increase the number of planes. In the second case, we analyze the effect of orbit altitude on the performance of satellite network. The orbit altitude is divided into 8 groups from 800 kilometers to 1,500 kilometers. Other parameters are the same in each group. In figure 7, as the height increases, the capacity have little change, but the delay increases, which results in reduction of the network performance. In the third case, we analyze the effect of phase effect on the performance of satellite network. According to the first formula, we set 6 groups of phase effect from 0 to 5. Other parameters are the same in each group. In figure 8, as the phase factor increases, the capacity decreases, but delay first decreases and then increases. It can be explained by the polar region. In the end, let's conclude what we have done. Firstly, we build a fixed satellite topology. Then, capacity and delay model are added into NSL. Next, we use MDMC to evaluate the network performance by calculating the minimum delay and the maximum capacity. Finally, we set 3 different cases to study the performance difference of satellite network. From the results, MDMC is appropriate to evaluate and compare the performance of aerial satellite networks. That's all my report. Thank you for your attention.
The title of my paper is Attribute to Quek. It is a completely unsupervised algorithmic framework for learning the Latin representations for nodes. In Attribute to Quek, we have adopted a attribute processing method similar to GCN that is taking the average of the features of the node neighbors as the feature of the node. My speech consists of 4 parts. The first part is an introduction to graph embedding. The second part is the analysis of research states. The third part is our model. The fourth part is future jobs. Introduction to graph embedding. When dealing with actual problems, information is usually organized into graphs. We need to learn useful information on the graph, but machine learning directly on the graph has certain limitations. Therefore, we need to perform graph embedding. That is, each node in the graph is represented as a low-dimensional, real-valued dense vector form. In this graph, nodes represent objects, edges represent connections between objects, and the colors of nodes represent the types of objects. In figure 1, it is the original picture. In figure 2, it is the result of graph embedding on the original graph. The graph embedding vector of this node contains semantic information, relation information, and the structural information of the nodes. At the same time, the distance between vectors reflects the similarity between nodes. The advantages of image embedding. First, it makes the feature no longer sparse, convenient as the input of the machine learning model, and it can be compressed. Vector calculation is simpler and faster. Graph embedding can be directly applied to common tasks in social networks, such as visualization tasks, node classification tasks, link prediction tasks, and so on. Here is an example of a visualization task. In figure 3 is a bubble diagram, and the figure 4 is the graph embedding of the bubble graph. The graph embedding vectors of the nodes that are symmetrical to each other are very close in the vector space, which means that they are very similar. Another application of graph embedding is the combination of graph embedding and a recommendation system. Wide deep is composed of a shallow wide part neural network and a deep part multi-layer neural network. The output layer uses softmax or algis regression to synthesize the output of the wide and deep paths. Summarize the advantages of this structure in one sentence. The wide part helps to enhance the memory ability of the model, and the deep part helps to enhance the generalization ability of the model. This is the graph embedding progress, and the figure 5 is the wide deep recommendation model. This part is research case analysis. Deep work is based on random walk method. The early influential graph embedding method is deep work, proposed in 2014. Its main idea is to perform random walks on a graph structure composed of items to generate a large number of item sequences, and then input this item sequence as training samples into Word2Vec for training to obtain the embedding of the items. As shown in figure 6, the entire deep work algorithm follow can be divided into 4 steps. Figure A shows the original user behavior sequence diagram. By B builds an item concorrelation diagram based on this user behavior sequence. It can be seen that the edges between items A and B are generated. The reason is because user UE has purchased item A and item B successively, so a directed edge from A to B is generated. After converting all user behavior sequences into edges in the items correlation graph, the global items correlation graph is established. Figure C uses a random walk to randomly select the starting point to regenerate the item sequence. Figure D finally inputs this item sequence into the Word2Vec model to generate the final item embedding vector. Two disadvantages of random walk method. The first is if two nodes are similar but are far apart in distance, they will not interact during the random walk process, and therefore will not be learned by graph embedding into similar vector representations. In figure 7, the similarity of distant nodes is difficult to capture. The second is methods such as deep work and later Node2Vec can only capture the structural information of graph, while the actual node also have various attribute information. Figure 8 is a social network diagram. In this diagram, nodes represent people and the items in the rectangle box represent people's hobbies. In our model, we call this node information as the attributes of the nodes and calculate the similarity between nodes according to them. In this scenario, Ben and Paul have the similar attributes and their friends have similar attributes. Although far apart to each other in the network, we also think that Ben and Paul have the high degree of similarity. We can see that the nodes not only have structural information but also attribute information such as human hobbies. GCN is proposed in 2017, was inspired by the convolutional neural network and designed a feature processor that can extract the features of the node attributes. But it is a semi-supervised algorithm and requires a certain number of labeled nodes. To sum up, random walk methods, it's difficult to capture the similarity of distant nodes. The random walk method cannot handle the attribute information of the node. GCN is a semi-supervised learning method that requires some labeled node to participate in training. The goal of the design model is to capture the similarity of distant nodes, ability to learn the similarity between the attributes information of the node. It is an unsupervised learning method that does not require nodes to be labeled. This part is the initial model. Question 1. How to judge whether two distant nodes are similar? Solution is by calculating the distance between the attribute vectors of these two nodes. The two nodes with the larger distance are not similar. In the following example, A and B are more similar because the distance between their attribute vector is smaller. The figure 10 is an example of attribute vector. Specific method is calculating as if the Euclidean distance of any two node attribute vector. Figure 11 is equivalent to converting the original image into a fully connected image. In this way, the similarity of any two nodes in the graph can be obtained. Question 2 is how to learn the similarity between the attribute information of nodes. Because we use the attribute vector to calculate the node similarity, the similarity of the node attributes is already included into obtained similarity. The formula 1 is a node distance calculation formula. Question 3. How to design an unsupervised learning method. The solution is use random sampling to generate node sequence and then use Wavelet model for training. Step 1 is build a fully connected weighted graph. Greater the weight, the greater the probability of sampling. Sampling n times from each node, n is the sequence length. Figure 12 is the process of random sampling to generate a node sequence. As the figure shows, we perform random sampling based on the similarity of nodes, so we can think that the nodes in the same sequence are all similar to each other. Step 3 is input the node sequence into Wavelet training to get the graph embedding results. This step is the same as the last step of deep work. Figure 13 is input Wavelet model for training. The ball is the main structure of the initial model, but there are problems such as too high computational complexity of the model. Therefore, I optimize the model these aspects. The OP1 is expand the similarity of the node to the similarity of the neighborhood to improve the quality of the model output. The OP1 we do it by expand the similarity of the node to similarity of the neighborhood. Specific method is take the average of the attribute vector of node U and then the attribute vector of U's neighbors to use it as a new attribute vector of node U, and distinguish first-order neighbors and the second-order neighbors. For example, in a citation network, the nodes are different articles. The edges are the citation relations between the articles. The attributes of the node are the keywords in articles. It can be extracted in a unified way and represented by a series of numbers of equal length. We assume that the attribute of the node is already in our train data. Note that we have to do is to generate key attribute vectors for each node. In particular, the case attribute vector of U is generated by average attributes of nodes that are at distance exactly k from U in general network. U is a node in the network. And equation 4 is the weight calculation formula. In this way, the similarity weight of the node pair is changed from 1 to 3. The following connected weight graph is changed to a 3-layer 4 connected weight graph, and the weights are calculated from its own similarity, first-order neighbor similarity and second-order neighbor similarity. We construct a weighted multi-layer graph to save the similarity between attributes of the nodes. After obtaining the 3-layer weighted fully connected graph, you can jump between different layers and then perform node sampling according to the weight. The sampling process remains the same as before. In this way, we extend the similarity of node attributes to the similarity of node neighborhood. This part is experimental results. We use the data is classification text of Coral dataset. Node mean, paper edge mean, citation relationship, label means article category. Therefore, we use the latent representations then by different graph embedding model as the input to TSNE as a result. Each node in core network is mapped as two-dimensional vector. Another common application of latent representation of network is classification. In this section, we first use attribute Quek and some other state-of-the-art network embedding technologies to learn meaningful latent representations of core network and use neural networks to divide these latent representations into training and test sets for classification tasks. Potential representation of the nodes becomes attributes, which are used to training a supervised neural network classification. It can be seen that performance of attribute to Quek at OP1 better. It is a reasonable result because when OP1 attribute to Quek extends the similarity of nodes itself to the neighborhood similarity of nodes, the model gets more effective information, so it can perform better. The future work is increasing the dataset and conduct more horizontal comparison experiments and optimize the code, increasing concurrency and improve efficiency. And apply the result of graph embedding to the recommendation system. This is my reference. Thanks.
Hello everybody, my name is Zhang Xiuxian. I'm a postgraduate in communication from the Nanjing University of Post and Telecommunications, and I have spent the past 2 years to research blockchain and artificial intelligence. Today, I'm going to present a paper titled Hashgraph-based Federated Learning for Secure Data Sharing as a key technology of connected intelligence. The importance of artificial intelligence has increased rapidly. It is important to note that the most critical challenge is the secure data sharing, which is stored in different areas and belongs to different organizations. With this in mind, a Hashgraph-based federated learning for secure data sharing model is proposed to protect user privacy and detect the dishonest model provider. In this paper, a common distributed data sharing scenario with multiple parties is considered. The system can be divided into 2 parts: the blockchain platform and the communication network. The blockchain platform adopts Hashgraph consensus to reduce the consensus time and network overload. Especially, the blockchain platform is used to record the local model retrieval, with the raw model parameters are stored in local. The availability of local models and all the sharing data events, which can trace the use of data for further audit. The communication network takes charge of data communication. All users who want to provide data sharing service can apply to join the blockchain platform. A data sharing requester launches a request to the blockchain platform. The blockchain will check whether the request has been processed before. If there is a hit, the request will be forwarded to the node that has cached the results, and the cached results are then sent to the requester as a reply. In construct, a new federated learning request with data categories and incentive mechanism will be published in the platform. Then the data provider participated in the blockchain will choose whether join the federated learning or not, according to the matched degree of the data they have, with the data requested and the incentive mechanism. All nodes participated in the federated learning are regarded as committee nodes, which are responsible for driving the consensus in the blockchain. In this paper, we consider the problem of privacy preserving and dishonest model provider checking in data sharing process with decentralized multiple parties. In order to protect privacy of local model, homomorphic encryption is used to encrypt the local model and then transmit the encrypted model to the next node. The local model transmits among the committee nodes. All the committee nodes check the availability of the local model and vote on the model. Only more than 2/3 of the committee nodes agree the local model is legitimate. The Hashgraph is adopted in this paper. It is different from the previous blockchain. The nodes of the Hashgraph package the transactions into events instead of blocks to the communicate with other nodes. Lots of problems of the transaction blockchain can be solved in Hashgraph, such as long consensus time, the lack of concurrent processing mechanism to meet the large-scale scenario application, and too high transaction cost in small transactions. The Hashgraph is an asynchronous Byzantine fault tolerance system, with no node can prevent the network from reaching consensus or modifying data after consensus has been reached, and it can achieve bank-level security. Events as the smallest unit of the Hashgraph mainly include timestamp, transaction information, self-parent hash, other parent hash, and digital signature, where the self-parent hash is the hash of the last event on this node, and the other hash is the hash on the last event on the other node. Transaction information is the main content of the event, mainly include local model retrieval, sharing data information, the availability of local model. In more detail, the local model retrieval is the record of the retrieval information of the local model. The sharing data information contains data categories and the data quantity, and the availability of local model is the record of the supporting to the model or not. The core technology of Hashgraph are the communication mechanism, gossip protocol, and the consensus algorithm virtual voting. The communication mechanism uses a gossip protocol. In the gossip protocol, the node randomly selects another member and sends data which is known in this node but not known in the selected node to the selected node. When the node receives the data containing new information, it first executes all the new transaction information that has not been executed and checks in the availability of the local model, and then repeats the same process by selecting another random node. Therefore, the protocol of gossip spreads exponentially until all the nodes receive the event. Before introduce the process of virtual voting, we introduce some concepts first. Witness. The first event created by the nodes is called witness. Round. The witness is the beginning of the round for the node. Seeing. An event Y could see event X only if event Y can find X by the pointer or hash. Strongly saying, when all paths of event Y could find event X goes through supermajority of nodes called Y strongly see X. Famous witness. If a witness of round R can be seen by supermajority of witness of next round, then the witness of round R is the famous witness. The virtual voting processing is divided into 3 steps: divide rounds, decide famous witness, determine round received, and consensus time. Divide round. When the event can see supermajority of witness of last round, then the event is the beginning of the next round. Decide famous witness. If the first round witness X can be seen by the witness on second round, then the second round will vote yes to X, and witness a third round to collect the vote. If the number of yes votes is more than the majority notes, the event X is a famous witness. Determine round received and the consensus time. Assuming that all witnesses in round R has been determined whether they are famous witness or not. The receiving round of event X is R. When all known witnesses of round R can see the event, find all the event Y that can see X on the path from X to all famous witnesses in R. Then the median or time step of event yi is the consensus time. The local model omega I t is trained using deep learning based on its own data on each device at time t and transmit the encircled model parameter this omega I t to the other participants of the blockchain platform to check the availability of the local model. The weight coefficient is calculated as this, where K is the local number of datasets provided by our users who participated in the federated learning, and Ki is the number of i's datasets. As such, Ni is the number of the committee nodes who support omega it, and the I is the number of the committee nodes who participated in the federated learning. It is worth noting that once the consensus is complete, the system model omega t is the system parameter model omega t is confirmed as this. The performance of the proposed method with the detection of dishonest provider is compared with the conventional federated learning, where the total number of the local model provider I is 10, and assume that there is one dishonest provider. Then divide the dataset into non-fragments. Simultaneously, randomly generate a dataset as the dishonest provider's dataset, and assume that the proportion of the data provided by the dishonest provider is 0.2. It is worth to notice from this figure that the performance of the federated learning based on Hashgraph is better than the conventional federated learning in the aspect of prediction accuracy, F-measure, and recall. As shown in this figure, it is obviously that the more proportion of the data provided by the dishonest provider, the lower accuracy of the federated learning will be in the conventional federated learning, but it makes no difference in the proposed federated learning. Thank you for your attention.
Hello everyone. What I'm talking about today is the design of Fast-SSC decoder for STT-MRAM channel. I will share this decoder from the introduction, preliminary, decoding algorithm, decoding architecture, performance, analysis, and summary. The polarization code proposed by Eric is based on the channel polarization, which is an error control coding scheme. Polarization codes are the first to be able to prove that the channel complexity is reachability through mathematical message. From this picture, we can clearly see the characteristics of the polarization code. A part of the polarized channel is a perfect channel approaching 1. We use it to transmit information bits. And the rest of the complex noise channel that tend to 0 transmit frozen bits to increasing the probability of character decoding. The basic unit of STT-MRAM is a magnetic tunnel junction. Control and acted to MTG through a MOS transmitter. In this paper, the writing error P0, P1, and read interference error P-right of the STT-MRAM channel are simulated by combining the transmission probabilities of the BAC channel. In the JMC channel, R0 and R1 present the low state and the high state of the MTG unit, so that R0 and R1 follow the Gaussian distribution of mean value and variance. The following is the decoding algorithm part. The figure A on the left is the decoding tree of the SC decoding algorithm. We take the code length 60 as an example to study, and the right is the decoding rule. When the node V is activated, it concludes alpha V through F operation and transmits the result to V left if V left is not leaf node. V left is activated and the F operation is until the left child is leaf node. If V left is leaf node, beta V left, performing hard decision on alpha V left, then transmit it to experience node V. Conclude alpha right by J operation and transmits alpha V right to V right. If V right is a leaf node, perform a hard decision on alpha right. Conclude beta estimates beta V right and transmits it to V. According to C operation, the C operation is performed to calculate beta V and transmit to PV. In order to reduce the decoding steps, the leaf node is defined as V0 with the frozen bits and the rate 1 with all information bits. The remaining nodes are subdivided into IEP and SPC node. The levels of the rate 1, rate 0 nodes are all frozen bits, which means the bit estimate of the rate 0 node is all 0. The levels of the rate 1 are all information bits. Its estimates by hard decision as this formula. It can be sensed that the evaluation of the rate 1 node is the single bit of the LR value. The last leaf of the IEP nodes is an information bit, and the other nodes are frozen bits. It has only two decoding results, or 0 and or 1. Next is the SPC node, which is a more complex node. The first leaf of the SPC node is a frozen bit, and the others are information bits. It is necessary to perform a threshold detector and get the parity check by this formula. Then, if the parity constraint is satisfied, the estimated bit is generated by reusing the beta weight concluded above. The least reliable bit is found and flipped if the parity constraint is not satisfied by this formula. We design a decoding based on the Fast-SSC algorithm. We transmit the channel LR to the processing element, which is used to perform a decoding of F, G, C, and special nodes. The decoding process is operated by the controller, which decides whether the data transmitted to the PE is reading from the registry or memory. If the result of current state are not used immediately by the next state, it will be stored into memory. We use the one comparator, one XOR gate, and a combination logic to implement F operation. The G operation has two inputs, alpha and beta. When beta is 0, add two LR numbers. When beta is 1, subtract first value from the next. For IEP nodes, they only use the sum of the sum bar to estimate the code words. To ensure that the bit width does not affect the accuracy, they use 0 field mode for IEP, with coordinate LMV is less than 16 to avoid the performance degradation. According to the character of SPC nodes, absolute value of the LRs is to be sought when the number of LRs is large. The sourcing complexity is high, which limited the operation frequency of this model. We constrain the length of the SPC to 4. This model selected the smallest LRs. When D0 is 1, it denotes that the estimates of bit 0 in SPC nodes is need to flipped. According to the characteristics of Polar code, this paper split the date for nodes with a codeless of NV more than the 64, and which can reduce data writing time and decoding latency. Among them, We use the FI, denotes the F operation, use the input areas of the current code. The special phase extraction is all follows. Perform F0 of the root node, and the result is stored in the registry. And then continue F1 of the root node, and the result is stored in the internal area memory. Then the root node is not used, but activated the next node. After reading the combined date of registry and memory, execute F0, that is, obtain alphabet of its left child node by the F operation, and store it in memory. Return to root node. Execute F2 and F3, and store the result in memory. Then execute F1. Using the area of the left child of the root node, the resulting area is combined with the F0. And finally, execute F64 to alphabet, with the NV is 32 nodes. And the subsequent lower years still follow the Fast-SSC for decoding. In the case of the same hardware, the decoding can reduce decoding process. For 10 clocks, I split takes the node date. For nodes with NV more than the 64, the C and the J operations use the same rule to spare the area. Compare the register to update the date in time to ensure the accuracy of the counter distillation. In this paper, the channel area is content-defined with 60 bits include one fractional bit. Simulation results show that decoding performance with the context-defined date is very close to that of the floating point performance in terms of BER and BRER. We compare two decoders with different PE numbers. On comparison, it is found that the operating frequency of the two decoders have reached 167. Resource consumption comparison is shown in this figure. 32 PE has a significant reduction. We designed a high throughput fast FFC decoder for STT-MRAM channel. Synthesize it on the FPGA. Simulation results show that the fixed point decoding performance is very close to that of the floating point algorithm. By supplementing the node date and adjusting the data performances in order to optimize the architecture, the proposed decoding reduces the complexity of data selection and the decoding latency. Okay, thank you everyone.
Good morning, professors. My name is Nadi. I come from Shandong University of Science and Technology. I'm very pleased to be here to join this forum. The topic of my presentation is pipeline BP polar decoder with a novel updated scheme. My presentation will include these 5 parts. First, research background and significance. Second, research status. Third, research contents. And the fourth, research basis and feasibility analysis. And the last, summary and log outlook. First, some background I will introduce for this paper. Combined with the following background, I chose this topic. For reliable signal transmission, over the past half-century, coding scientists have put forward many kinds of error-correcting codes, such as tuple code, LDPC code, and so on. But all practical coding methods have failed to reach the capacity limit of channel transmission given by Shannon in 1948, also known as Shannon limit. Eric put forward a kind of coding research result called polar code in this paper, which is the first coding scheme proved to reach Shannon limit and binary discrete memorialized channel with definite construction method and low code complexity. The Huawei main polar code became the coding scheme of 5G control channel EMBB as a strong competitor of 6G standard. Polar code is of great significance to its research. Polar code is still in the primary stage of development from the beginning to the present. Every step from coding and decoding algorithm to hardware implementation to practical application needs further study. During the process of hardware implementation, the structural flexibility and hardware resource utilization of polar code BP decoder are still insufficient, which lead to its lack of competitiveness in practical application. Further research is carried out to obtain a BP decoder with more balanced overall performance. And next, we can simply understand the current situation and the development of polar code. As shown, the polar code decoding algorithm mainly includes BP algorithm and SC algorithm. Among RCSC, RLSC algorithms are used to improve decoding performance. For early stop, they are G-base RMACA and WIB. Then, SMS, FFD are in hardware architecture. The main contents on its paper are as follows. We will discuss BP decoding algorithm and the pipeline polar BP decoder architecture. In BP decoding, here is a BP decoding factor diagram with a list of 8. The BP process unit consists of a left node and the right node, and this is BP information update formula. This prior to decoding, the LR received from the channel is transmitted to the left information of the rightmost column node of the factor graph L. where the right information of the leftmost column node of the filter graph is determined by the position information at the time of encoding, and all the remaining nodes in the filter graph are initialized to 0. The initialization of node information in the decoder is as follows. This is the left node, and this is the right node. When the BP decoder reaches the preset maximum number of iterations, Rmax, UI can calculate the LLR value of the leftmost column node according to the following volume and stop decoding, like this. And now, it's pipeline polar BP decoder architecture. As shown, this is conventional polar code BP decoder architecture. The number of BCB required for BP decoder with a parameter 10, 24, 512 is this 51 and 20, and the decoding process delay and the BCB utilization are 10R plus 1 and 0.1. This is decoding architecture for pipeline BP non-parallel code. The number of BCB required for polar BP decoders with parameter 10, 24, 512 is 18, and the decoding process delays are 1040R plus 512, and the BCB utilization was 0.49. And our proposed updated schedule scheme are as follows. This is the original update schedule. We can see that the original scheme requires a second iteration after the completion of the first iteration. And now, this is our improved schedule process. Our proposed update schedule scheme can start the second iteration at the same time as the first iteration. Therefore, the improved scheme can effectively reduce delay, reduce storage resource consumption, and improve the resource utilization. And then, a BP decoder architecture of pipeline polar code is obtained, like this. The number of BCB required for a polar BP decoder with parameter 1024, 512 is 18. This is its process delay. It's 512R plus 512. The BCB utilization can reach 100%. Now it's our research basis and feasibility analysis. According to the all above analysis, we have tested the experimental data. Next, let's discuss the experimental data structure. In performance analysis, the following figure shows that the polar code parent is 10,512 and the decoding performance simulation result and the AWGN channel and BPSK modulation node. When the maximum number of BP iteration is 40, the decoding performance of proposed NOV polar code BP decoder decreases slightly in the low signal to noise region, but it is very close to the decoding performance of the traditional BP decoder in the high signal to noise region. The following table shows the number of BCB usage, BCB utilization, and the decoding delay of proposed NOV polar code BP decoder and the different code lengths. We can clearly see, compared with FFD, the overall performance of our proposed scheme is greatly improved. The number of BCB required is the same, but the decoding length can be reduced 50.7%, and the BCB visibility increased by 15.6%. In terms of hardware resource, the following table shows the comprehensive simulation result of polar code BP decoder and 183 and 143 quantization schemes when the polar code parameter is 1024 and 512 and the scaling factor is 0.9375. Our scheme can be reduced by 38.9% in registers and 25.8% in block memory, and our working frequency can be increased by 1.9 times and 2.1 times. Finally, each hour's working plan. Summary and outlook. First, according to the BP existing decoder architecture design, this paper analyzes and compares its information update schedule process and put forward an improved update schedule scheme. Numerical results show that this scheme can obviously reduce the decoding delay of each iteration in the decoding process and improve the utilization rate of the BCB of the function unit. Third, and the second, based on the proposed schedule scheme, a corresponding pipeline polar BP decoder architecture is designed. The simulation results show that the architecture can greatly reduce the overhead of storage resource in registers and block memory, and improve the frequency of decoder BCB the same cost of function units. And the third, aim of this paper is to reduce hardware resource overhead and improve hardware resource utilization of polar-code BP decoder by improving and optimizing the proposed BP decoder design can provide great flexibility and regularity, and can achieve a better balance in decoding performance, frequency, lattice, and utilization. Also, we have some outlook for our work. First of all, the proposed hardware architecture of NOV polar-code BP decoder doesn't add the early iterative stop creation in its design, so the hardware performance of the decoder with this creation is also the content and need to be. Then, only one BCB per order is used in the actual design of the BP decoder. However, the overall performance of the decoder can
Hello everyone, my paper title is Recommendation-Based Heterogeneous Information Network and Neural Network Model. I will start my discussion from three aspects. Introduction, the proposed model, and experiment. Part 1 is Introduction. The rapid development of the Internet area has brought the huge amount of information resources, which makes users can't accurately obtain the information they need. Therefore, as a kind of information retrieval tool in the Internet area, the recommendation system has developed rapidly. Currently, heterogeneous information network (HIN) are widely used in recommendation systems due to their advantages in complex information modeling. In Figure 1, we can see that the HIN contains multiple types of entities connected by different types of relations. Meanwhile, network representations learning, which aim at learning the low-dimension representations vectors of each node, has shown certain potential in structural feature extraction. Heterogeneous information network representations learning is an extension of the homogeneous network representation learning, which emphasizes both on the complex structure and rich semantics, and has shown effectiveness in many recommendation tasks. I will introduce the related work on heterogeneous network representations learning. HIN representation learning research method has such as method based on random walk, which have metapath to vect, HIN to vect, HINE, and the second is method based on decomposition, such as HEREC, AMPE, and the third is method based on neural network, such as BLMNE. And the classical recommendation algorithm is the matrix factorization algorithm, such as collaborative filter. However, the matrix factorization algorithm will generate cold start problem. We try to improve the effect of recommendations by adding auxiliary information. For example, MA proposed adding auxiliary data such as social relations to matrix decomposition to recommend users. Ling not only considered scoring information but also its comments information to it. In recent years, representation learning has become a hot research. At present, most online services are typical heterogeneous information networks, which can make full use of various rich semantic information to make personalized recommendations for users. Chuan Shi proposed HEREC algorithm, and Huan Zhao proposed meta-graph algorithm. Bingbing Hu proposed MCREC algorithm, and Yongfeng Zhang proposed GRL recommended model. Although the existing recommendation method based on heterogeneous network representations learning has improved performance to a certain extent, they still face some challenges. One is that in most existing HRN representations learning work, there is a large amount of noisy data in the MetaPath instance, generated by the random walk of the MetaPath, which will reduce the performance of the recommendation system. Two is most existing recommendation algorithm only model the interaction between users and items, and can't make full use of the MetaPath will reach auxiliary information in HIN, which makes the recommendation result lack of interpretability. Part 2 is the proposed model. In order to solve the above problems, we propose a recommendation system based on heterogeneous network representations learning and a narrow network model. The main ideas of this article are as follows. In order to fill out noisy MetaPath instance, the matrix factorization algorithm is used to generate the latent factors for users and items, which are future used to calculate the similarity between nodes, guide the MetaPath-based random walk, calculate the cosine similarity between nodes, and the top key MetaPath instance with high score are selected. We propose a narrow network recommendations framework that combines LSTM with attention mechanisms. This framework can learn the three feature representations of user item and MetaPath information and make predictions after the integration of the three to improve the recommendation effect. And we define the three definitions such as heterogeneous information network and the network schema and the MetaPath. And the table 1 is the examples of MetaPath. Let me introduce overall framework. The main framework of this paper is the combination of heterogeneous information network representation learning and narrow network. First, matrix factorization algorithm is used to evaluate the MetaPath instance generated by MetaPath-based random walks. For each MetaPath, the instances are assessed by average similarity between adjacent nodes along the instance path, and top key instances are selected as pre-training vectors for the recommendation system. Then, a narrow network recommendation framework combine LSTM and attention mechanisms in Figure 2 is proposed. This framework can learn the feature representations of user item and MetaPath and make prediction by using MLP so as to jointly improve the recommendation performance. And part 1 is selection of MetaPath instance. A MetaPath instance is a sequence of nodes generated by random walks, MetaPath. The average similarity of the edge in the MetaPath instance can be taken as its score. Then the top key instance can selected as the input data. We use the matrix factorization on each tab. Are as follows. And then MetaPath-based random walk on heterogeneous networks is based on following transition probability. And the third is similarity measure for node pairs on a MetaPath instance, and the end is MetaPath instance score. The part 2 is user and item embedding. As lookup can simplify the operation and low time complexity, we use lookup to produce the user embedding and item embedding. Formally giving a user item pair, user item. Let EU and BI denote these one-hot representations. The lookup operation is implemented as follows. The part 3 is MetaPath embedding. In order to capture particularly semantic for different MetaPaths, each MetaPath is processed separately. As LSTM is good at sequence modeling and the attention mechanism can obtain the importance of each MetaPath instance, we combine the LSTM and the attention mechanism to produce the MetaPath instances embedding, content embedding, and path instance with distribution. Then concatenate path instance embedding obtained by the attention mechanism and content embedding to obtain a single MetaPath embedding in Figure 3a. Similarity: different MetaPaths playing different roles for determining the node's relevance. So we introduce the attention mechanisms to put different weight on each MetaPath embedding. Each individual MetaPath embedding is fused into one final MetaPath representation in Figure 3b. First, use the combination of LSTM and attention mechanism to obtain the embedding of a single MetaPath. First, we use LSTM to learn the sequence embedding of path instance are as follows. And then use the attention mechanism to put different weights on each MetaPath instance embedding. And then the end is concatenate the attention mechanism's resource O and the content embedding UP together to form a single MetaPath embedding PJ. The second is obtained different weight of different MetaPath embedding. Different MetaPaths play different roles for determining the node's relevance. In Figure 4, we use the attention mechanism to obtain the weights of different MetaPaths, CE and CN. The third is interaction of users, item, and MetaPath embedding. In Figure 4, we concatenate the MetaPath embeddings with users embedding and item embedding as follows. And the end is model prediction. In Figure 4, we feed the out to the MLP component in order to model the complex nonlinear interaction among the three embeddings are as follows. Defining objective functions for models optimization is the key to learning a good recommendation model. In our task, the objective for an interaction UI can be formulated as follows. And part 3 is experiment. We use Mullen's datasets, which contains data for users and their ratings on movies, include 943 users and 1,682 movies. The MetaPaths used are shown in Table 2. The user an item had an embedded demotion and of 128, a random walk path length of 10, and a window size of 3. And then we consider compared with the following method, such as item KNN, a classic collaborative filtering method that recommends similar item based on previous item, and MF standard matrix factorization method, and SVD filter, and FMG rank, and then HEIEC, a recommendation method based on heterogeneous network embedding, which is fused with matrix method for recommendation. The first is overall performance. We divide the entire dataset into a training set and a test set. We use different proportion of data, 20%, 40%, 16%, and 18% as the training set. We use ranking-based accuracy, precision, recall, and F1 value as to the matrix to evaluate the recommended performance of our model. In Figure 5, the result shows that 1. Our proposed method is always superior to all comparison models. Compared with other HIN-based method set, our model uses a method based on heterogeneous network representations learning combined with LSTM and attention mechanism to fuse the 3 aspects of user, item, and metapath information for recommendations tasks, making recommendations result more accurate. 2. The model's performance improves as the training dataset increases. And the second is metapath instance selection. In order to verify the effectiveness of the metapath instance selection method, we compare the performance F1 score between model with filtered and unfiltered metapath instances as data input, as shown in Figure 6. The results show that by filtering out the noisy instance, the recommendation performance can be effectively improved the recommended model. Third is metapath attention weight visualization. The attention weights for different metapath is visualized in Figure 7, which shows the impact of different metapaths on recommendations performance. We can find that for the moveless dataset, the UMDMU metapath takes more weight than other metapaths. Therefore, we believe that some metapaths can improve the performances of the model more than others. In the end, is my summary. In this paper, we proposed a recommendation system based on heterogeneous network representation learning and narrow network model. We selected metapath instances with better quality as the pre-training vectors of the recommendation system. We combine the LSTM and attention mechanism to learn the 3 aspects of user, item, metapath information. Use the MLP to predict so as to improve the recommendation effect. In the experiment, we prove that our model improves the performance of the recommendation system by concatenate with users' items and metapaths embedding. The embedded vector information is enriched, which not only improves the recommendation effect, but also makes full use of the metapath information to enhance the interpretability of the recommendation result. That's all. Thanks.
Hello everyone, my name is Shijing Dou. I'm from Nanjing University of Posts and Telecommunications. Today, I'm very pleased to share my paper with you. The title of my paper is Performance Analysis of Video Flow in Mobile Edge Computing Networks based on Stochastic Network Calculus, which proposes a performance analysis framework for the end-to-end video flow in MEC networks based on SNC. Today, I will make my presentation from the following three aspects. The first one is introduction. It will introduce the research scenario and method SNC used in this paper. The second one is system model. It is the main part of this paper. And the last one is performance analysis, which shows the conclusion and results. First, let's enter the introduction section. In this part, I will introduce the scenario in this paper. The first one is the increasing number of users. With the increasing popularity of mobile terminal devices, data flows related to the different business applications are also on a constant rise. The delay due to the increasing number of users in the network poses a great challenge in its capacity to handle high throughput. The second one is mobile edge computing. MEC networks provide the end users with closer computing service. They can reduce the end-to-end delay and energy consumption. This means that the storage and computing resources in the edge nodes are deployed closer to the user terminal. MEC networks can carry the data of a variety of applications, and end-to-end performance analysis of these services serves as a benchmark for the efficient planning of network resource allocation and routing strategies. The third is software-defined network technology. SDN is introduced into MEC to flexibly control the forwarding of the network traffic, leading to the random routing of data flows. The last one is stochastic network calculus. We use SNC as a tool to derive the delay formula of video flow in this paper. Actually, end-to-end performance analysis of different applications in various scenarios has been studied using Queen theory already. Then, why we use SNC other than Queen theory in this paper? The results obtained by the Queen theory are the average analysis results in steady states. Moreover, the Queen theory has a specific requirement of restricted distribution of the arrival process of data flows and service process at the spheres, so it is not suitable in the scenario used in this paper. While SNC is a good tool, it can also deal with Queen system for analysis of delay backlog and other QoS of computer networks. It uses alternate algebras to transform complex nonlinear network system into an analytically tractable linear system. It overcomes the shortcomings exist in the Queen theory. Besides, some kinds of flows can tolerate several loss and delay, such as the multimedia flow, so stochastic service guarantee is more important to these flows for better utilization of reuse games in network. Another reason is that some networks, such as wireless network and multiple access networks, can only provide stochastic service guarantee. So, SNC is a very good tool for us to use in the scenario in this paper. In this part, I will introduce the basic knowledge of SNC. In this picture, we can see that the AT is the arrival process of the flow, and alpha t is the arrival curve of the flow. It should be bigger than AT. ST is the service process of the flow, which is the cumulative service of serves the flow can obtained during the time interval from 0 to t, and beta t is the service curve of the flow, which should be smaller than the ST. We also have the cumulative departure traffic of the flow during the time interval from 0 to t, and the delay is the horizontal distance between the arrival process and the departure process. The backlog is the vertical distance between the arrival process and the departure process. There are many useful properties of SNC. They can help us to simplify our derivation. First one is concatenation theory. It is used to combine the service process of multiple serial nodes into one node's service process, and the leftover service is used to obtain the service process of data flows without interference. The superposition theory is used to combine the multiple arrival processes on one node into one arrival process. Then, let me introduce the system model of the paper. The data of different applications are transmitted through multiple network elements. A network element can be a terminal, a router, an access device, or other equipment. Each network element corresponds to a node in this picture. The communication link between any two nodes can be a single hop or multi-hop. A node can have multiple neighboring nodes. As long as these neighboring nodes are within the transmission range, they can be chosen to create a communication path. TF represents the through flow. It is the intended data transmitted through an established path. IF represents interference flow. It is the data sharing the nodes on the same path used by the TF, and the services provided by the nodes in that path are also shared. It means IF may affect the performance of the TF. SDN is introduced into the MEC network in this paper, so multiple routes are used by the same pair of the source and the destination nodes. Each TF selects its path randomly to reach its destination node and complete its task, so the selection of each hop is random. We defined two interference scenarios. The first one is data flows from different service chains reaching the agent on the path of TF and needing to share data processing at the agent. Just like agent 1 in the picture may need to share service to TF and interference follow A. The second one is data flows on the current agent having the same next hop choice as the through flow, and need to share data processing on the next agent, like agent 4 and agent 7 may need to share the data processing service to TF and interference follow B. In this paper, we assume three types of data flows in the system: VoIP, video, and FTP flow with decreasing priority. Primitive priority scheduling is adopted for efficient scheduling of these different data flows. This is our mathematical model. We use SNC to set up a mathematical model for the analysis of arrival and service process of data flows in the MEC network. We configure the agent nodes as service nodes, the path selected by the TF in the system model as the service chain in the mathematical model. In our analysis, we assume to fix video flow as the TF, VoIP flow and FTP flow are RFS. Due to the random nature of routine in the MEC networks, we introduce probability parameters in our proposed analysis model to characterize this randomness. These are our analysis methods. The performance analysis process of through flow is shown in the picture. C flow represents the through flow. A and B flow represent interference flows. First, we need to get the cumulative traffic of these two interference flows, which may interfere with the performance of the through flow on each node. Then, we use the superposition theory to combine these two cumulative traffic into one. Afterwards, we use leftover service to get the cumulative service provided to the through flow on each node. Then, we use concatenation theory to combine the service curves of multiple nodes into one. Finally, combined with the through flow arrival curve, using mini-algebra convolution and deconvolution to get the performance upper bound of the through flow, that is the delay bound of video flow in this paper. Here is the notations used in this paper, which will be used in the formula derivation in next part. These three notations are represent the probability of outflow from other service chains arrives at node J. The probability of outflow transmits from node J to node J plus 1. The probability of outflow needs to be processed by node J respectively. Theta represents the free parameter. Then, let's enter the derivation process. First is the arrival process. The arrival process of video flow is shown like this. The arrival rate of video flow is constant, and we represent this constant by R. Then we need to analyze interference. Because the priority of VoIP flow is higher than the video flow, it will affect the performance of the video flow. However, the priority of FTP flow is lower than the video flow. It cannot affect the performance of video flow. The cumulative interference traffic which affects the performance of video flow is like this. The third one is the service process of the video flow. According to the interference analysis, we can get the service curve of the video flow. And the last one is the delay analysis. Combine the arrival process and the service process, and according to the Chernov's inequality, we can get its delay upper bounds. At last, we will enter the performance analysis section. First, we compare the simulation delay result of single node with the delay upper bound predicted by the mathematical expression derived in this paper. We can find that they can match very well. It evaluates the accuracy of the delay upper bound derived in this paper. Then, we want to explore the factors affecting the delay performance of video flow. First, we think the number of hops experienced by the video flow is a factor. So, we change the number of hops, and then we can find that the end-to-end delay upper bound increases by the increasing of number of hops. Besides, we think the probability parameters of VoIP flow and FTP flow may also affect the delay performance of video flow. So, we fix the number of nodes and change the probability parameters of VoIP flow and FTP flow respectively. we can observe that when the probability parameter set of the VoIP flow increases, the delay upbound of the video flow significantly becomes larger. Meanwhile, when the probability parameter set of the FTP flow is changed, it does not influence the performance of the video flow. Why? Because the priority of the VoIP flow is higher than the video flow. The increase in probability parameters of the VoIP flow indirectly grab more service resources. Therefore, the performance of the video flow becomes poor. However, the priority of the FTP flow is lower than the video flow. The change in its probability parameters do not affect its performance. The above is the entire content of my paper. My presentation is over. Thank you all for listening.
Hello everyone, I'm Jiang Enfu. I will present the article, A Bell-inspired Smart Access Algorithm for Large-Scale Self-Organizing Wireless Networks. Today, I'll mainly divide it into 4 parts. First, background, second, system model, third, algorithm introduction, and finally, simulation results. The first part is the background. With the explosive growth of the number of nodes, in order to implement efficient access without always neat collision between nodes, the nodes need to have a high degree of self-organization in the current network. As it is known that self-organizing phenomenon is a very common phenomenon in nature. It is caused by the cooperation interaction between individual organisms. Sticker-merge is an information coordination mechanism for biological individual autonomy. It is an indirect coordination mechanism between agents or individual behaviors. In the absence of central control and direct contact with communication, the group implements information interaction symmetry through some methods, such as coordination. Therefore, it can be considered to resolve the collision problem that is easy to happen among the distributed multi-nodes competing to access the same channel in the future companies and the changing network environment. The second part is system model. The picture shows my system model. It is a self-organizing wireless network composed of multiple distributed nodes. Learning from the sticker-merge mechanism, a coordination mechanism between a large-scale number of nodes in the wireless network is implemented, which is based on the formula communication interaction. It provides an effective solution to reduce collision that is prone to occur in the network. A similar cooperation mechanism model is established between nodes in a wireless network through the sticker-merge cooperation mechanism model. Each node is regarded as a different agent. As the agent's behavioral state changes, and if the state reaches a central condition, it will send broadcast information in the network. This process is regarded as the agent's living formula in the environment. The other agents adjust their current behavioral state through receiving the information. The second part is algorithm introduction. According to the established cooperative mechanism model, we propose a bell-inspired smart access algorithm. This algorithm is a candle for desynchronization that is implemented in the paper by means of combining the comparative magnetizing model and the phase oxidation model in synchronization theory. As shown in the picture, the state of each node at time t is regarded as a phase value theta t. Each node had an initial phase value. The phase change of a node is similar to the oscillation of a phase oscillator. When the phase value of the node reaches 2 pi, the node can access the channel to transmit data packets and infer the adjacent nodes of the current state by the way of sending broadcast information. If a node receives the broadcast information from the adjacent node during the phase change, it will extract the information and immediately send the broadcast information to the adjacent node as well. At the same time, the node updates the phase to avoid collision with the node that is transmitting data. According to the process, this paper divides the algorithm into 3 stages. The first stage is phase initialization. As shown in the picture, each node sets up an initial phase value which is represented as 4 nodes. And then we consider the service type and the remaining energy as factors to calculate the initial phase. The second part is phase change. The phase value of node is a direct rate and time varying function. Then the phase change should satisfy as 4 nodes. When the theta reaches 2 pi at time t, the node N will send adjacent nodes broadcast information including the phase value of the current node and the estimated time of the Approximate channel. Then it starts transmitting data packets and resets its phase value to 0. If the node N receives broadcast information from an adjacent node during the phase change, it will immediately carry out the phase update and send a broadcast information including the phase value of our current node. The second is the phase update. After receiving the broadcast information from adjacent node M, the node N extracts the information to carry out the phase update. The phase of the update node is expressed as 4 nodes. The last part is the simulation results. In the experiment, we determine whether a collision has occurred by calculating the phase difference between each node and the remaining nodes. The phase difference between the 2 nodes is randomly distributed between 0 and 2 pi at most of time, which indicates that the probability of packet collision between nodes is very small. It shows that the comparison graph of the collision probability. In the PSATS, nodes are able to adjust their behaviors to avoid sending data packets at the same time. Therefore, the probability of collision is relatively smaller than the CSMA-CA mechanism. And then it's a comparison graph of the channel throughput performance. It can be seen from the figure 8 that the channel throughput performance of the PSATS is overall improved by about 12% to 15% compared to the CSMA-CA mechanisms. The next, it is a comparison graph of the access delay performance. It can be seen that when the number of competing nodes is small, the access delay of the PSATS is slightly longer than the CSMA-CA mechanisms. However, With the increase in the number of competing nodes, the time for back-off retransmission and the back-off reading is increasing, and the delay is also increasing in the CSMACA mechanisms, while in the BSAA, the increase in the time spent by the nodes on the phase change and the phase update is not very large. That's all. Thanks for your listening.
Hello everyone, my name is John Pippin. Now I want to share with you the paper research on network fault detection and the diagnosis based on deep Q-learning. Firstly, I want to share with you that our goal is to solve the problem of how to do network fault diagnosis efficiently. This slide shows a picture of heterogeneous wireless network scenario, and we realized that in order to improve the efficiency and quality of service of the network convergence and the development of the heterogeneous network has become inevitable. It's a challenge to detect and diagnose the various network faults efficiently in the complex network environment. So, to solve this problem, a network fault detection and diagnosis algorithm based on deep Q-learning is proposed. Combine deep learning and reinforcement learning model to classify network faults. We can classify some obvious network states via using less features and filter irrelevant or redundant features at the same time. What exactly do we want to achieve? First of all, we classify the network failures. There will be multiple network failures, such as interference, link failures, and so on. And in our scenario, each network state is represented by multiple key performance indicators. We can set KPIs, including RSRP, DCR, and so on. When adopting a new KPI, there is a cost, and we want to implement implementation that using failure key performance indicators to determine the right network failure. So we want to maximize accuracy and minimize cost. In order to use the reinforcement learning algorithm to solve the problem of the network fault identification, it's necessary to model the problem of network fault identification as a micro-decision process. As shown in figure, when agent is carrying out the task, it first interacts with the environment to generate a new state, and the environment returns a reward. As the cycle goes on, the agent and the environment constantly interact to generate more new data. Reinforcement learning algorithm to generate new data through a series of action strategies and environment interaction, and then use the new data to modify their own action strategies. After several iterations, the agent will learn the action strategies needed to complete the correct fault diagnosis. we define S as a state contains of a set of simples xy, and the currently selected feature set K. And we define the xy as the simple in dataset, a vector x as the value of the feature set K composed of K performance iterators, and y as the target label. And we also define C is defined as the cost function. When when we choose a new feature K, and the cost is CK. And we also defined the action as A contains AC and AK. AK represents selecting a new feature that has not been selected before, and AC means to use a classification action to predict what category the sample belongs to. And we provide that if A is equal to AC, the event will be end. And we want to the reward function R should be designed to achieve the correct classification and seek the optimal subset features based. So in each step the reward function can be defined as below. When the action of the agent is selected as the classification action, and the selected action is the final correct classification, the reward is defined as 0. And when the action of the agent is selected as the classification action, but the selected action is the wrong classification, the reward is defined as -1. And in the set case, when the action is selected as the feature selection, the reward is defined as the minus mu multiply CK. So that's how we define our scenario from the perspective of micromodel. And the most typical model-free reinforcement learning is Q-learning. In ordinary Q-learning, when the state and action space are discrete and the dimension of them is not high, Q-table can be used to store the Q value of each state action pair. While when the state and the action space are high dimensional continuous, it's not practical to use Q-table. In the actual network fault diagnosis process, the network structure is very complex, and the corresponding causes of the network fault are also very diverse, and the parameters of master network performance are also various. So the state and the action space studied in this paper is high-dimensional continuous. Using Q-table is not realistic. So the method of this paper is to use the DQN to turn the Q-table updating problem into a function fitting problem, and the similar state can get the similar output action. We can see the DQN loss function in this slide. the DQN using a neutral network function with theta as an approximator called a Q network. One Q network can be iteratively treated by minimizing the loss function of the decision sequence. We can see the Q tacket is what. And the DQN training process is shown in figure. It uses two key technologies. One is the experience reply. The function of the experience reply is mainly to solve the problems of correlation and non-static distribution. The specific method is to store the transfer samples obtained from the interaction between the agent and the environment at each time step in the playback memory unit, and randomly take out a mini batch of them to train when training is needed. And this treatment breaks the correlation between samples and makes samples independent of each other. The other one is the fixed target value network. Calculating the network target value requires the use of existing Q value. Now a network with slow updating rate is used to provide this Q value. This improves the stability and convergence of training to make the algorithm performance more stable. Establish two neutral networks with the same structure. One network that has been always updating neutral network parameters, and the other one network for updating Q values. We can see mainnet and target net. Initially, assign mainnet parameters to target net. Then, mainnet continues to update the neutral network parameters, where the target net parameters are fixed. After where the mainnet parameters are assigned to target net, and so on. In this way, the target Q value is stable for a period of time, which makes the algorithm update more stable. And now we can see the experimental results. The data obtained by setting the simulation environment is input into the DQN model as input parameters, and the reward is obtained through continuous iteration. The accuracy of the network fault classification is shown in Figure 1 and Figure 2. As can be seen from the Figure 1, in the initial stage of training, the average reward convergence rate is very fast and then tends to be stable. And since we narrowed it is reached from -1 to 0, this efficiently overcomes the numerical explosion. It can be seen from Figure 2 that the optimal classification accuracy rate is very high. And during the initial training, the DQN algorithm selects almost all features to make classification decisions. which makes the accuracy rate increase rapidly. As the number of iterations increases, the number of selected features will gradually decrease. After a period of exploration, the agent will find the smallest subset composed of important features, and as the number of iterations increases later, the total number of choice changes slowly and tends to be stable. In this process, the agent will continue to change the best subset of failure combination to improve accuracy. But it has not improved a lot. Therefore, the classification accuracy rate increases rapidly at the beginning and actually converges to a stable value after reaching high accuracy. And we can see from the figure 3 is the simulation result for selecting different cost factors mu. From the picture, we can see that the smaller mu is as the smaller the absolute value of the cost generated by feature selection. Then the agent will iterate more times to search for the optimal feature subset. At first, the algorithm selects the most features, then as the number of iterators, and then as the number of iterations increases, then it starts finding redundant features. The speed of the filtering redundant features at mu is equal to so the speed actually as the curve stabilizes, the difference in classification accuracy between the two is very small, so we can choose to control the best choice and convergence speed by adjusting to cost factor mu. Actually, simulation results show that the method can achieve more accurate network fault diagnosis and prediction. However, it requires a lot of computing resources during the training process, and the training time is slow. So other enhancement technologies can be studied in the future to improve the performance.
Hello everyone, it's my honor to be here for sharing my paper. The topic of my paper is single satellite interference loss location based on 4-coin efficiency beam. In the part 1, we will introduction the satellite, whether in daily life or in special activities, such as wide patrons, military operation, earthquake relief, and other special activities. Mobile communication systems are essential for communication. The satellite mobile communication has a characteristic of wide coverage, good reliability, and no geographical limitation, which makes up for shortcomings of the ground mobile communication system and improves robustness and reliability of the communication system. Internationally, The development of satellite mobile communication system is very rapid. A number of global or regional mobile communication systems, including Iridium, Eurostar, and international mobile communication satellites, has been established. In personal communication, transportation, satellite mobile communication systems are widely used and providing an effective means of communication in all terrain conditions. With the continuous development of satellite communication technology, more and more spring resources are used, and the interference received by satellites is increasing. In the military and the civilian field, the position of satellite interference source has always been a hot issue. The single satellite interference source of the orbital multi-beam satellite has a small Doppling shift due to its operation in the current orbiter and can be observed by single star. And the commonly used satellite observing method cannot be used. The interference source location method based on single strength of the interference source and interference location are small. By establishing the relationship between heterogeneous and inference source pointing direction. For the existing single star interference source location algorithm, the error pointing angle, satellite orbit height, single source power, and other data measured by the tracking telemetry system have different degree of deviation, which influence the result of the pointing direction of interference source. At the same time, the particle swarm algorithm used in the position algorithm proposed by the predecessors tend to be unable to converge due to random generation of the popular position. The correct result cannot be obtained when calculating incident direction of the inference source. This algorithm is designed for the orbital satellite mobile. According to the limitation of the existing single star interference source, a new interference source location method is designed. In the part 2, we will introduce the previous method. The antenna gain is the reduction of the power density of the signal generated by actual antenna to the ideal radiating element at the same point in space under the condition of equal input power. That is, describes the ability of antenna radiating the input power directly. The establishment of the point beam radiation model can be approximated by a function provided by literature, which related the angle between the incident direction of the single source and the central axis of the beam to gain provided by the spot beam. Assume that the closed 3-point beams around the interference source beam 1, beam 2, and beam 3 have received the interference source signal. When the interference source signal passes through the uplink, there will be free space transition loss, atmospheric multipulse effect, and other losses. Set all losses on the uplink to air, and the duration progress is following. If you have interest, you can learn about it. The method proposed by the predecessor to use the interference source singular strength received by 3-point beam inferred by interference source and antenna gain pointing model to establish the direction equation has good accuracy. However, in the actual measurement process, because the point beam center point measured by the trunk telemetry combination measure error and has a great influence on accurate direction of the
interference source. Therefore, it's possible to find the four-spot beam closest to the interference source from outside the trigger to dimension flows. The diamond region composed of two equatory triggers can be used to study the location of the interference source. Using this model, four sets of orientation equations established by three space-borne beams that are not identical can be obtained. If the four sets of the orientation equations are treated as four dependent origin systems, which is equivalent to four measurements of the same physical qualities, the paper proposed to use the least squares method to preprocess the data obtained. It's possible to obtain a result that is less affected by the error, reduce influence of the error on the position, and enhance the robustness of the systems. It is assumed that the four spot beams around interference source each receive different inference resource single strengths, and the incident direction of the first set of interference source singulars are calculated as alpha and beta. Assume that three are different degrees of derivation for the four sets of the interference source points. After process the four sets of dating using a least square method, the interference source direction with the degree of derivation between the minimum and maximum can be obtained. Find a pointing that satisfies the following formula. As shown in the first picture, the surface of the orange PSO algorithm, there is a no-convergence condition in which the fitness is always fixed, and this is also a case where the local optimum cannot reach the optimal solution. All the most observed searches provide coverage. It has a large impact on the results when averaging. The no coverage disappears, and each resource covers after 14-5 iterations, and the coverage speed is faster, improving the reliability of the previous method. It can be seen from the 100 average result in the table. The original algorithm is less reliable, and its correct origin is listed in the table. In this experiment, the result of the change when the center of the point beam is changed from 4 to 6 degrees assimilated, and the change obtained by the original method and the proposed method are compared. As shown in the figure, the maximal error of the angle alpha is about 0.1 degree, and the maximal error of beta is about, which is much better than the original method, and when the error is larger, since the satellite is a GEO orbit, the origin error will prove an error of about 100 kilometers. The covers in the previous two graphs are linked by 20 experimental results. According to the experimental results, it proves that the proposed method has better optimalness and reliability than the original method in the presence of measurement deviation. In conclusion, the existing stoichiometric beam satellite interference source localization algorithm scale for unitized three-point beam that receives the interference source singular around the interference source to establish a link equation, and establish an alternate gain point model to associate the interference source pointer with the alternate gain. The link equation is changed to an orientation equation, and it is solved by an efficient particle swarm optimization algorithm. Combined with the satellite operation data and Earth information, the operation of the interference source can be accurately obtained under ideal conditions. However, the algorithm has deficiencies. In view of the limitation of existing algorithms, This paper proposed an improved algorithm using 4 different sets of equations composed of 4 spawn beams, and proposed an improved particle swarm optimization algorithm for solving the set of directional equations. When the particles are measured and initialized, the reliability and the convergence speed of the particles are improved. In the treatment of the 4 sets of the indifferent source pointing date, the paper uses the least squares method to diminish the error influence. That's all. Thank you for listening.
Hello everyone, my name is Feng Lijie. I come from Nanjing University of Posts and Telecommunications. Today, I will introduce data reconstruction via deep convolutional neural network. This is my outline. Firstly, this is background. Secondly, is data pre-processing. Thirdly, is spectrum data reconstruction. And fourthly, experiments and evaluations, and finally is our conclusion. With the increasing number of seeing tasks, the amount of data transmitted by the satellite spectrum seeing system becomes enormous. However, this spectrum seeing data may not be transmitted due to limited transmission capability and a huge amount. The methods to solve the problem of limited data transmission is data compression and downsampling and data reconstruct. Our motivation for this work is as follows. Firstly is to investigate a spectrum data super-resolution reconstruction with the aid of deep convolutional neural network. Secondly is to generate high-resolution spectrum data, relying on data reconstruction in the presence of low-resolution spectrum data. Thirdly is to improve the reconstruction quality with the aid of the super-resolution reconstruction method. And then we introduce data pre-processing, and this is very important progress. Firstly, we sense the spectrum data and transmit them, which is low-resolution spectrum data. And then we pre-process the spectrum data and input them into our constructed model for training to complete high-resolution spectrum data reconstruction. And finally, we output the high-resolution spectrum data that is constructed. And this progress is our system model of spectrum data reconstruction. And this figure is our data pre-processing in trailing phase. Because the real-world spectrum data are collected and stored as PSD value to reduce the impact of random noise and avoid direct reconstruction of the PSD value. The sensed data should be pre-processed, include normalization and zero interpolation, and then the normalized HR a spectrum date is considered as a HR spectrum image, which can be used as a trailing label. Moreover, for trailing purposes, the HR spectrum image can be converted into LR spectrum image while downsampling. Moreover, the LR spectrum image will be inserted with 0 by the factor of D in both time domain and frequency domain. And here, we take the factor D is equal to as an example. The specific zero interpolation can be shown in this figure. And then we will input them into our model for trailing. This is data preprocessing in the testing phase. The data preprocessing in reconstruction phase only relies on normalizing the acquired LR spectrum data and carries out zero interpolation operation. And then the pre-prepressed the frequency data can be fed into the model to achieve recovery and reconstruction. The whole progress as shown in this figure. And then we introduce spectrum data reconstruction. As this figure, DCN besides spectrum super resolution reconstruction. In order to perform super resolution reconstruction of the spectrum, besides on DCNN network, a 3-layer neural network is constructed, which can process a large amount of data and learn an end-to-end future mapping between LR spectrum and HR spectrum. Moreover, it can also estimate missing HR information in the LR spectrum in order to complete reconstruction of spectrum data. Relying on spectrum data pre-processing, spectrum future extraction, and non-linear mapping, and final reconstruction. The specific model is as shown in this, and their formulation as this follows. In order to evaluate the reconstruction performance, the mean square error is used as the loss function of DCN, which can indicate the distance between the reconstructions and the targets by loss scholars, and can be formulated as this, where uppercase K denotes the total number of spectrum trailing samples, and this downcase K is the sample number, and this Y is a set of real-world HR spectrum, and this X is corresponding set of LR spectrum. The model reconstruction performance is evaluated with the aid of mean absolute error named MAE value, which is used to evaluate the normalized PSD error between the real-world HR spectrum and the reconstructed, and can be given by this, and M is the total number of frequency points, and N is the total time slot, and this Y is the normalized PSD, in the real-world HR spectrum, and this Y is the normalized PSD of the reconstructed spectrum, and I and J are the frequency point and the time slot, respectively. And then we introduce experiments and evaluations.
This is experiment platform introduced. Firstly, the experiment platform is Intel Core CPU, and this GPU is NVIDIA RTX 2080 Ti. This is CPU. This is my computer configures, and the convolutional neural network is built on the TensorFlow framework. The dataset used in the experiment is the spectrum data of the GSM 1800 downlink, ranging from 1820 to 1875 amperes, and the time span is 2 weeks. The minimum sampling interval in the frequency domain of the dataset is 200 kHz, and the minimum interval in the time domain is 1.8 seconds. And this is hyperparameters. This is evaluation of different convolutional kernel combinations. In the width of the network is changed by the number of convolutional kernels, which means that the width of the network refers to the number of convolutional kernels per layer. In order to output the complete reconstructed spectrum, the number of convolutional kernels in the last layer is flexed to 1. This is 4 groups of different convolutional kernel number combinations are selected. From this table, it is clear that the performance of the network improves as the network width increases, but considering the time overhead, the wider the network width costs more time. So our hyperparameters as follows. This is evaluation of different convolutional kernel size, because different convolutional kernel sizes are also evaluated. The convolution kernel size of the second layer is set to, which adds non-linearly features without loss of resolution, improves the network expressions ability, and reduce the computational complexity. And this is my hyperparameters with different convolutional kernel size. And then the effect of the model dips is analyzed. The model parameters are shown in this table. And finally, we choose 3 layers model for our model dips, which is 915. And then this is reconstruction performance. The compression results of the reconstruction performance of the model are shown in this figure. It can be seen that the convergence speed of the 3 layers network is slightly faster than that of the 4 layers network, and the 3 layers network has a better performance than that of the 4 layers network in MAE. And finally, this is our conclusions. Firstly, we examined the data reconstruction for low-resolution spectrum data. And the second is 3-stage beside the spectrum data reconstruction method was conceived, consisting of data pre-processing, model training, and data reconstruction. Third is we showed that the designed model can generate high-resolution spectrum data in terms of low mean absolute error. That's all. Thank you for your attention.